When we step outside on a clear night and look up at the star-filled sky, a question naturally comes to mind. How big is the universe? How far does space actually stretch? Is there an end to it all? Or does it go on forever? Tonight, we embark on an extraordinary journey through scale and distance, exploring the unimaginable vastness that surrounds us on all sides. Picture yourself standing in your backyard. You can see perhaps a few miles in any direction before the horizon blocks your view. Now imagine zooming out, higher and higher, until your entire city becomes just a tiny dot. Keep going until your country looks like a small patch. And then your entire planet Earth becomes nothing more than a pale blue speck floating in the cosmic dark. But we have only just begun our journey outward. Beyond Earth lies a solar system so vast that light itself, traveling at over 600 million miles per hour, takes more than 4 hours to cross from the sun to its outer edges. Yet this enormous space we call home is merely a grain of sand compared to what lies beyond. The universe contains mysteries that challenge our very ability to comprehend size and distance. We will travel together past billions of stars, through galaxies that contain more suns than there are grains of sand on all the beaches of Earth. We will venture into the space between galaxies, where darkness reigns supreme across distances so great that the fastest spacecraft ever built by humans would take millions of years to cross them. Along the way, we will discover how scientists measure these incredible distances, using clever tricks with light and mathematics to peer deeper into space than any human eye could ever see. We will learn about the strange relationship between distance and time, where looking farther out means looking farther back, until we reach the very edge of what can be observed. Our journey will take us to the limits of human knowledge, to places where our best theories begin to break down and wonder takes over. We will ask whether the universe has boundaries, whether it goes on infinitely, and what it might mean for something to be truly without end. This is not just a story about size and distance. It is a story about human curiosity, about our deep need to understand our place in the grand scheme of existence. Every measurement we will discuss represents countless hours of careful observation, brilliant insights, and the combined efforts of generations of astronomers and physicists who dared to ask the biggest questions of all. The numbers we will encounter are so large they stretch the limits of language itself. We will speak of distances measured in light years, where a single light year equals nearly 6 trillion miles. We will discuss galaxies containing hundreds of billions of stars, each potentially hosting worlds of their own. We will explore regions of space so vast that if our entire Milky Way galaxy were shrunk to the size of a coin, the observable universe would still stretch for miles in every direction. Yet even these mind-boggling scales represent only what we can see. Beyond the observable universe may lie regions even more vast, perhaps infinite in extent. Some scientists suggest that our entire visible cosmos, with all its billions of galaxies, might be just one tiny bubble in an endless ocean of space and time. As we begin this cosmic voyage, remember that every photon of light reaching your eyes from the stars has traveled across the vacuum of space for years, decades, or even centuries to reach you. You are literally seeing into the past, witnessing the universe as it was long before you were born. The deeper we look into space, the further back in time we see, until we approach the very moment when the universe itself began. So settle in for this exploration of the infinite. Let your imagination expand as we journey from the familiar to the incomprehensible, from the scale of planets to the scale of creation itself. The universe awaits, vast beyond measure, and full of wonders that will leave you breathless with amazement. To understand how big the universe truly is, we must first learn how astronomers measure the vast distances between celestial objects. This might seem like an impossible task. After all, we cannot simply stretch a tape measure across the cosmos or send a spacecraft to count miles between stars. Yet through centuries of careful observation and brilliant mathematical insights, scientists have developed ingenious methods to map the universe with remarkable precision. The challenge of measuring cosmic distances is unlike anything we face in everyday life. Imagine trying to determine how far away a distant mountain peak is without ever leaving your backyard. You cannot walk there to pace off the distance. You cannot throw a ball and time how long it takes to reach the mountain. All you can do is observe and use the tools of mathematics and physics to deduce the answer. This is precisely the situation astronomers face when studying the cosmos. Consider the simple act of reaching for a glass of water. Your brain instantly calculates the distance to the glass, using visual cues like size, perspective, and the slight difference between what your left and right eyes see. But what if that glass were sitting on a table a mile away? Your depth perception would fail completely. Now imagine that glass is actually a star sitting trillions of miles away, appearing as nothing more than a faint point of light. The challenge becomes almost incomprehensible. Yet this is exactly what astronomers must accomplish. They must determine distances to objects so far away that their light has traveled for years, centuries, or even billions of years to reach us. They must measure the distances to stars whose light left them before humans existed on Earth. They must probe the depths of space to galaxies so remote that we see them as they appeared when the universe itself was young and dramatically different from today. Our journey through cosmic measurement begins close to home, in our own solar system, where distances are relatively small and measurement techniques are most reliable. From Earth to the Sun stretches approximately 93 million miles, a distance so fundamental to astronomy that it has become our first cosmic yardstick. We call this distance 1 astronomical unit, often abbreviated as AU. This measurement forms the foundation for all other distance calculations in space. To appreciate the scale of even this first step on our cosmic distance ladder, imagine traveling from Earth to the Sun at the speed of a commercial airliner. Flying at 500 miles per hour without stopping, the journey would take over 21 years. If you could drive the distance in a car at highway speeds, the trip would take more than 100 years of continuous driving. Yet this enormous distance is merely the first rung on a ladder that extends to the very edges of observable space. But how did we first determine this crucial distance to the Sun? Early astronomers could not simply point a laser at the Sun and measure the bounce-back time. The Sun is far too bright and hot for such direct measurements, and the technology simply did not exist. Instead, they used the elegant dance of planetary motions observed over many years. By carefully tracking how Venus appears to move across the face of the Sun during rare transits, and combining these observations with the geometric relationships between planetary orbits, astronomers in the 1700s were able to calculate our distance to the Sun with surprising accuracy. The transit of Venus provided one of astronomy's first truly international scientific collaborations. Expeditions were sent to remote corners of the Earth to observe these rare events, which occur in pairs separated by over a century. Captain James Cook's famous voyage to Tahiti in 1769 was primarily an astronomical mission to observe a Venus transit. From these global observations, combined with careful mathematical analysis, astronomers determined that the Sun lay roughly 93 million miles away. This early measurement was remarkably close to our modern value, differing by only a few percent. The achievement represents one of humanity's first successful attempts to measure truly astronomical distances, proving that careful observation and mathematical reasoning could unlock the secrets of cosmic scale. It demonstrated that the universe, despite its vastness, was not beyond human comprehension. Today, we have refined this measurement using radar signals bounced off Venus and other planets, as well as precise tracking of spacecraft as they journey through the solar system. When we send a radio signal to Venus and measure how long it takes to return, we can calculate the distance between Earth and Venus with extraordinary precision. Since we know the orbital relationships between the planets, this gives us an incredibly accurate measurement of the astronomical unit. Modern radar measurements, combined with spacecraft tracking and laser ranging to the Moon, have determined the Earth-Sun distance to within a few hundred miles. This represents a precision of better than 1 part in 10 million, an accuracy that would be like measuring the distance from New York to Los Angeles to within the length of a football field. The result is a distance measurement accurate to within a few hundred miles, an incredible precision given the 93 million mile span we are measuring. This level of accuracy has become essential for modern space missions, where tiny errors in distance calculations could cause spacecraft to miss their targets by thousands of miles. Once we know the distance to the Sun, we can begin to measure distances to nearby stars, using a technique called parallax. This method relies on a simple principle you can demonstrate right now. Hold your finger at arm's length and look at it first with your left eye closed, then with your right eye closed. Notice how your finger appears to shift position against the background. This apparent shift is called parallax, and it occurs because you are viewing your finger from two slightly different positions. The parallax effect is everywhere in our daily lives. When you drive down a highway, nearby objects like fence posts seem to zip by quickly, while distant mountains appear to move slowly or not at all. This difference in apparent motion is another form of parallax, and your brain uses it constantly to judge distances and navigate through the world. Astronomers use the same principle to measure stellar distances, but instead of using the distance between your eyes, they use Earth's orbit around the Sun as their baseline. They observe a nearby star from one side of Earth's orbit, then wait 6 months and observe the same star from the opposite side of Earth's orbit. The star appears to shift slightly against the more distant background stars, and this tiny shift allows astronomers to calculate the star's distance using trigonometry. This technique requires extraordinary patience as well as precision. Astronomers must wait a full 6 months between observations to maximize the baseline for their measurements. They must account for Earth's motion through space, the gravitational effects of other planets, and countless other factors that could affect the apparent position of stars. They must also ensure that their instruments remain calibrated to incredible precision over these long time periods. The parallax method sounds simple in principle, but in practice it requires extraordinary precision. Even the nearest stars show parallax shifts smaller than 1/1000th of a degree, an angle so small it would be like trying to measure the width of a dime from over 2 miles away. To put this in perspective, the parallax shift of the nearest star is smaller than the width of a human hair, viewed from a distance of 10 miles. This incredible precision became possible only with the development of sophisticated telescopes and, more recently, space-based observatories that can make measurements unaffected by Earth's atmospheric turbulence. Ground-based telescopes, no matter how large or well-designed, must peer through miles of shifting, turbulent air that constantly distorts the apparent positions of stars. This atmospheric interference limited parallax measurements for centuries. The breakthrough came with space-based telescopes, beginning with the European Space Agency's Hipparcos mission in the 1990s. Operating above Earth's atmosphere, Hipparcos could measure stellar positions with unprecedented precision. The mission measured parallaxes for over 100,000 stars, revolutionizing our understanding of stellar distances and the structure of our local galactic neighborhood. The European Space Agency's Gaia mission, launched in 2013, has taken stellar parallax measurements to an entirely new level. This remarkable spacecraft has measured the positions and parallaxes of over 1 billion stars with extraordinary precision. Gaia's measurements are so accurate that it could detect the apparent motion of a coin on the surface of the Moon as viewed from Earth. The nearest star to our solar system, Proxima Centauri, shows a parallax shift of just 768 thousandths of an arcsecond. This measurement represents one of the most precise angular measurements ever made, requiring technology that can detect changes in stellar positions smaller than the resolution of the human eye by a factor of several million. From this tiny measurement, astronomers calculate that Proxima Centauri lies approximately 25 trillion miles away. To put this distance in perspective, if you could drive a car at highway speeds directly to Proxima Centauri, the journey would take over 28 million years. If the Sun were the size of a basketball, Proxima Centauri would be another basketball sitting over 4,000 miles away. The light we see from Proxima Centauri tonight left the star over 4 years ago, when the current president was not yet in office, and many current high school students had not yet been born. This star, our very nearest stellar neighbor, is so distant that its light carries news that is already years out of date by the time it reaches our eyes. Such enormous distances quickly make miles meaningless as a unit of measurement. Instead, astronomers use light years. The distance light travels in 1 year. Since light moves at approximately 186,000 miles per second, a light year equals nearly 6 trillion miles. Proxima Centauri is about 4.2 light years away, meaning the light we see from this star tonight actually left the star over 4 years ago. Light years provide a more manageable way to discuss stellar distances, but even these units quickly become unwieldy when discussing galactic scales. For very large distances within our galaxy, astronomers sometimes use parsecs, a unit derived from parallax measurements. 1 parsec equals about 3.3 light-years, and represents the distance at which a star would show a parallax shift of exactly 1 arcsecond. Parallax measurements work well for stars within a few hundred light-years of Earth, but beyond this distance, the parallax shifts become too small to measure accurately, even with our best instruments. The Gaia mission can measure parallaxes for stars up to about 25,000 light-years away, but beyond this distance, even Gaia's extraordinary precision is insufficient. For more distant objects, astronomers must employ increasingly clever and indirect methods, each building upon the measurements that came before. This is where the cosmic distance ladder becomes crucial, with each measurement technique calibrated against the more reliable methods that work at shorter distances. One of the most important techniques for measuring greater distances involves standard candles, astronomical objects whose intrinsic brightness is known or can be determined. The concept is similar to estimating how far away a light bulb is by observing how bright it appears. If you know the actual wattage of the bulb, you can calculate its distance by measuring how dim it looks from your location. This inverse square law of brightness is fundamental to understanding cosmic distances. Light spreads out as it travels, so an object twice as far away appears 4 times dimmer, while an object 3 times as far away appears 9 times dimmer. By measuring how bright an object appears and knowing how bright it actually is, astronomers can calculate its distance with remarkable precision. In astronomy, certain types of stars and stellar explosions serve as these standard candles. Cepheid variable stars, for example, pulsate with a regular rhythm that directly relates to their intrinsic brightness. These stars expand and contract in regular cycles, growing brighter and dimmer in a predictable pattern. More luminous Cepheids pulsate more slowly, while less luminous ones pulsate more rapidly. By measuring the period of a Cepheid's pulsation, astronomers can determine how bright the star actually is, and by comparing this to how bright it appears from Earth, they can calculate its distance. This relationship between pulsation period and intrinsic brightness makes Cepheids incredibly valuable for measuring distances to nearby galaxies. The relationship between Cepheid pulsation periods and intrinsic brightness was discovered by Henrietta Swan Leavitt in the early 1900s through her careful study of variable stars in the Magellanic Clouds. Working at Harvard College Observatory, Leavitt analyzed thousands of photographic plates, carefully measuring the brightness variations of stars that changed over time. Leavitt's discovery was revolutionary because it provided astronomers with the first reliable method for measuring distances beyond our immediate stellar neighborhood. Her work laid the foundation for Edwin Hubble's later discoveries about the expanding universe and fundamentally changed our understanding of cosmic scale. Her work provided astronomers with a cosmic distance ladder, allowing them to measure distances to galaxies millions of light-years away. This discovery was so fundamental that it later enabled Edwin Hubble to demonstrate that the universe is expanding, one of the most important discoveries in the history of astronomy. Cepheid variables can be observed in galaxies up to about 100 million light-years away using the most powerful telescopes. Beyond this distance, individual stars become too faint to observe reliably, and astronomers must rely on even brighter standard candles. For even greater distances, astronomers use Type Ia supernovae as standard candles. These stellar explosions occur when a white dwarf star accumulates matter from a companion star until it reaches a critical mass and explodes with tremendous violence. The explosion completely destroys the white dwarf, releasing in a few seconds more energy than our Sun will produce over its entire 10 billion year lifetime. Because the mass at which this explosion occurs is always nearly the same, Type Ia supernovae always achieve nearly the same peak brightness, making them excellent standard candles for measuring distances to galaxies billions of light-years away. At their peak, these explosions can briefly outshine entire galaxies containing hundreds of billions of stars. The uniformity of Type Ia supernovae brightness makes them incredibly valuable for cosmological distance measurements. A Type Ia supernova in a galaxy 10 billion light-years away reaches the same peak brightness as one in a galaxy 1 billion light-years away. By comparing their apparent brightness, astronomers can determine their relative distances with high precision. The light from these distant supernovae is often so faint that it requires the most powerful telescopes on Earth and in space to detect and measure. Yet from these faint glimmers of light that have traveled across billions of years, and trillions upon trillions of miles, astronomers can determine not only distances, but also how the universe has evolved over cosmic time. Supernova surveys have discovered thousands of these stellar explosions in distant galaxies, providing a wealth of data about cosmic distances and the expansion history of the universe. These observations led to the surprising discovery that the universe's expansion is accelerating, driven by a mysterious force called dark energy. Another crucial tool for measuring cosmic distances comes from the expanding universe itself. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us, and more distant galaxies are moving away faster. This relationship, known as Hubble's law, provides a way to estimate distances to very remote galaxies by measuring how fast they are receding from us. Hubble's discovery revolutionized our understanding of the universe's nature and scale. Before Hubble, many astronomers believed the universe was static and unchanging. Hubble's observations proved that space itself is expanding, carrying galaxies away from each other like dots on an inflating balloon. The recession velocity of distant galaxies reveals itself through the redshift of their light. Just as the sound of a train whistle changes pitch as the train moves away from you, the light from receding galaxies shifts toward longer, redder wavelengths. This Doppler effect stretches the wavelengths of light from distant galaxies, making them appear redder than they would if the galaxies were at rest. By measuring this redshift, astronomers can determine how fast a galaxy is moving away, and from Hubble's law, they can estimate its distance. The faster a galaxy is receding, the more distant it must be. This relationship provides a powerful tool for measuring distances to the most remote objects in the observable universe. This redshift method allows astronomers to probe distances so vast that the light we observe left these galaxies when the universe was much younger than it is today. Some of the most distant galaxies we can observe appear as they were when the universe was less than 1 billion years old, compared to its current age of nearly 14 billion years. When we observe these distant galaxies, we are literally looking back in time. The light from a galaxy 10 billion light-years away left that galaxy 10 billion years ago, showing us how the galaxy appeared when the universe was only about 4 billion years old. This time travel aspect of astronomical observation allows us to study the history and evolution of the cosmos. Each of these measurement techniques has its own uncertainties and limitations, and astronomers must carefully calibrate one method against another to build a consistent picture of cosmic distances. This process, known as establishing the cosmic distance ladder, requires tremendous care and precision. A small error in measuring nearby distances propagates and grows larger when applied to more distant objects. The cosmic distance ladder resembles a chain, where each link depends on the strength of the previous one. If parallax measurements to nearby stars are incorrect, then Cepheid variable calibrations will be wrong, which will affect supernova distance measurements, which will impact our understanding of the universe's expansion rate. Each step must be carefully verified and cross-checked. The challenges of cosmic distance measurement have led to some of the most heated debates in modern astronomy. Different methods sometimes give slightly different results for the same distances, leading to what astronomers call the distance scale problem. Resolving these discrepancies requires ever more precise observations and careful analysis of potential sources of error. One ongoing debate involves the Hubble constant, which describes how fast the universe is expanding. Different measurement techniques give slightly different values for this fundamental parameter, leading to what cosmologists call the Hubble tension. This discrepancy might indicate new physics beyond our current understanding of the universe. Despite these challenges, the precision of cosmic distance measurements has improved dramatically over the past few decades. Space-based telescopes like the Hubble Space Telescope and the European Space Agency's Gaia mission have revolutionized our ability to measure parallaxes and calibrate standard candles. Ground-based surveys have discovered thousands of supernovae and variable stars, providing a wealth of data for distance calculations. Modern distance measurements are so precise that astronomers can now detect subtle variations in the expansion rate of the universe over cosmic time. These measurements have led to the discovery of dark energy, a mysterious force that appears to be accelerating the universe's expansion. Without accurate distance measurements, this fundamental discovery about the nature of our universe would have been impossible. The quest to measure cosmic distances continues to push the boundaries of technology and human ingenuity. Future space missions and ground-based telescopes will extend our measuring capabilities even further, allowing us to probe the universe's size and structure with unprecedented precision. The James Webb Space Telescope, launched in 2021, can observe individual stars and galaxies over 100 million light-years away, extending our distance measurement capabilities to new frontiers. New techniques are constantly being developed and refined. Gravitational wave detectors can now measure distances to colliding black holes and neutron stars, billions of light-years away. These measurements provide independent checks on other distance determination methods and open new windows into cosmic scale. Each new measurement brings us closer to answering that fundamental question of how big the universe really is. As our measurement techniques improve and our observations extend deeper into space, we gain a clearer picture of the cosmos and our place within it. As we conclude our exploration of cosmic distance measurement, remember that every number we will encounter in our journey through the universe's scales rests upon these ingenious techniques. The distances to stars, galaxies, and the edge of the observable universe itself all depend on this carefully constructed ladder of measurement, each rung supporting the next in humanity's quest to comprehend the true scale of creation. Measuring the cosmos is like stretching a ruler across eternity, and remarkably, we have learned to do exactly that. Now that we understand how astronomers measure cosmic distances, let us begin our journey outward from Earth to explore the vast region of space we call our local neighborhood. This cosmic neighborhood extends far beyond what we might initially imagine, encompassing not just our solar system, but a vast sphere of space containing hundreds of nearby stars, along with the invisible boundaries that separate our sun's domain from the realm of interstellar space. To appreciate the true scale of our local neighborhood, we must first grasp the immense size of our solar system itself. Most people picture the solar system as a relatively compact collection of planets orbiting not too far from the sun, perhaps like a small model that might fit on a tabletop. This mental image, while useful for understanding orbital relationships, dramatically underestimates the actual distances involved. If we were to scale the solar system so that Earth was the size of a marble, roughly half an inch across, the sun would be a sphere about 4.5 feet in diameter, sitting nearly 500 feet away. On this scale, Jupiter would be a ball about 5 inches across, located more than half a mile from the sun. Neptune, the outermost major planet, would sit almost 3 miles away, still just a marble-sized sphere in this vast scaled-down model. But even Neptune does not mark the true edge of our solar system. Far beyond the orbit of Neptune lies a region filled with icy bodies and comets known as the Kuiper Belt, extending outward to about 50 astronomical units from the sun. Beyond this, even more distant, stretches the Oort cloud, a vast spherical shell of frozen comets that may extend halfway to the nearest star. The Oort cloud represents the true boundary of our solar system, marking the region where the sun's gravitational influence finally gives way to the gravitational pull of other stars. This enormous sphere of space may extend outward to 50,000 or even 100,000 astronomical units from the sun. To put this in perspective, if Earth's orbit around the sun were the size of a quarter, the Oort cloud would be a sphere nearly 3 miles across. Light from the sun, traveling at its incredible speed of 186,000 miles per second, takes over 8 minutes to reach Earth. To travel to the outer edge of the Oort cloud, sunlight must journey for over a year and possibly much longer. The most distant objects in our solar system receive so little sunlight that they exist in conditions of perpetual twilight, barely warmer than the frigid vacuum of interstellar space. Within this vast solar system, we find a remarkable diversity of worlds. The inner planets, Mercury, Venus, Earth, and Mars, are small rocky bodies forged in the intense heat near the young sun. Mercury, closest to our star, experiences surface temperatures that soar above 800 degrees Fahrenheit during its day, hot enough to melt lead. Yet because Mercury has virtually no atmosphere to retain heat, its nighttime temperatures plummet to -300 degrees Fahrenheit, creating one of the most extreme temperature ranges of any planet in the solar system. Venus, often called Earth's twin because of its similar size, presents a hellish environment beneath its beautiful appearance. Hidden under thick clouds of sulfuric acid, Venus's surface bakes at nearly 900 degrees Fahrenheit, making it the hottest planet in the solar system despite being farther from the Sun than Mercury. The atmospheric pressure on Venus is nearly 100 times greater than Earth's, equivalent to the pressure found 3,000 feet underwater in Earth's oceans. Our own Earth, the third planet from the Sun, occupies what astronomers call the habitable zone, where liquid water can exist on a planet's surface. This Goldilocks zone, not too hot and not too cold, has allowed Earth to develop and maintain the complex chemistry necessary for life. Earth's atmosphere, with its protective ozone layer and greenhouse effect, maintains temperatures that keep most of our planet's water in liquid form, creating the conditions that have allowed life to flourish for billions of years. Mars, the red planet, shows evidence of a more dynamic past. Ancient riverbeds, lake basins, and mineral deposits suggest that Mars once had a thicker atmosphere and flowing liquid water on its surface. Today, Mars is a cold, dry world with an atmosphere so thin that liquid water cannot exist on its surface for long. Yet even in its current state, Mars remains one of the most Earth-like planets we know, making it a prime target for future human exploration. Beyond Mars lies the asteroid belt, a region containing millions of rocky fragments left over from the solar system's formation. These asteroids range in size from tiny pebbles to Ceres, a dwarf planet nearly 600 miles across. The asteroid belt might seem like a dangerous obstacle course for spacecraft, but in reality, the asteroids are spread across such an enormous volume of space that a spacecraft flying through the belt would be unlikely to come close to any asteroid without deliberately targeting one. The outer solar system belongs to the gas giants, massive worlds composed primarily of hydrogen and helium. Jupiter, the largest planet in our solar system, contains more mass than all the other planets combined. This enormous world could swallow over 1,300 Earths. Yet despite its immense size, Jupiter is composed mostly of gas and has no solid surface as we understand it. Descending into Jupiter's atmosphere, you would find the gas gradually becoming denser and hotter until it transitions into a liquid and then into exotic forms of matter under extreme pressure. Jupiter acts as a gravitational guardian for the inner solar system, using its immense mass to deflect or capture many comets and asteroids that might otherwise threaten Earth. Without Jupiter's protective influence, Earth would be bombarded far more frequently by potentially devastating impacts from space. Saturn, perhaps the most beautiful planet in our solar system, is adorned with its magnificent ring system. These rings, composed of countless particles of ice and rock, range in size from tiny grains to house-sized boulders. Despite their spectacular appearance, Saturn's rings are incredibly thin, typically only about 30 feet thick despite spanning nearly 200,000 miles across. If Saturn's rings were proportionally as thin as a sheet of paper, they would stretch across a continent. The ice giants, Uranus and Neptune, occupy the cold outer reaches of our planetary system. Uranus, tilted on its side so that it essentially rolls along its orbital path, experiences extreme seasonal variations as each pole alternately points toward or away from the Sun for over 20 years at a time. Neptune, the windiest planet in the solar system, experiences storms with winds reaching over 1,200 miles per hour, faster than the speed of sound on Earth. Beyond Neptune, in the Kuiper Belt, we find Pluto and thousands of other small icy worlds. Pluto, once considered the 9th planet, is now classified as a dwarf planet, but it remains a fascinating world with a complex system of moons and a thin atmosphere. The largest of Pluto's moons, Charon, is so large relative to Pluto that the two worlds essentially orbit around each other, forming a double planet system. The Kuiper Belt contains a treasure trove of pristine remnants from the solar system's formation. These icy bodies preserve materials and conditions from over 4.5 billion years ago, when the Sun and planets first formed from a collapsing cloud of gas and dust. Studying Kuiper Belt objects like Pluto, Eris, and Makemake helps astronomers understand the processes that shaped our solar system and the conditions that existed during its earliest epochs. But our solar system, vast as it is, represents only a tiny fraction of our local galactic neighborhood. The nearest star, Proxima Centauri, lies over 25 trillion miles away, a distance so great that if our entire solar system were shrunk to the size of a quarter, Proxima Centauri would still be over 10 miles away. Proxima Centauri is actually part of a triple star system called Alpha Centauri, located in the constellation Centaurus. The system consists of Alpha Centauri A and B, two sun-like stars that orbit each other, and Proxima Centauri, a small red dwarf star that orbits the pair at a great distance. Despite being our nearest stellar neighbors, the Alpha Centauri system is still so far away that the fastest spacecraft ever built by humans would take over 70,000 years to reach it. Recent discoveries have revealed that Proxima Centauri hosts at least 2 planets, including one that orbits within the star's habitable zone. This world, called Proxima Centauri b, is roughly Earth-sized and receives an amount of energy from its star that could allow liquid water to exist on its surface. However, Proxima Centauri is a red dwarf star known for violent flares that could strip away any atmosphere from nearby planets, making the actual habitability of these worlds uncertain. Within about 25 light-years of Earth, we find several dozen star systems containing nearly 100 individual stars. This local stellar neighborhood includes a fascinating variety of stellar types, from massive blue giants that burn through their nuclear fuel in just a few million years, to tiny red dwarf stars that could shine for trillions of years, far longer than the current age of the universe. One of the most interesting nearby stars is Sirius, the brightest star in our night sky. Located about 8.5 light-years away, Sirius is actually a binary star system consisting of a bright main sequence star and a white dwarf companion. The white dwarf, called Sirius B, is a stellar remnant about the size of Earth, but containing roughly the mass of our Sun. This incredibly dense object has a surface gravity so strong that a teaspoon of its material would weigh as much as a car on Earth. Another remarkable nearby star is Betelgeuse, a red supergiant located about 700 light-years away in the constellation Orion. Although not technically part of our immediate stellar neighborhood, Betelgeuse is close enough and bright enough to influence our local region of space. This enormous star is so large that if it replaced our Sun, its surface would extend beyond the orbit of Mars. Betelgeuse is nearing the end of its stellar life and could explode as a supernova at any time, possibly within the next 100,000 years. When Betelgeuse does explode, it will briefly shine as bright as the full moon and will be visible during daytime for several weeks. The explosion will release more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. However, Betelgeuse is far enough away that its supernova explosion, while spectacular to observe, will not pose any significant threat to life on Earth. Our local stellar neighborhood exists within a much larger structure called the local bubble, a region of space roughly 300 light-years across, where the interstellar medium is significantly less dense than average. This bubble was likely created by supernova explosions from massive stars that exhausted their nuclear fuel millions of years ago. The shock waves from these explosions swept up and compressed the surrounding gas and dust, creating a cavity of hot, thin gas that we now inhabit. The local bubble is surrounded by denser regions of interstellar gas and dust, creating a complex three-dimensional structure that influences the formation and evolution of stars in our galactic neighborhood. The Sun and Solar System are currently moving through this bubble at about 43,000 miles per hour relative to the surrounding stars, completing one orbit around the center of the Milky Way galaxy approximately every 225 million years. Within our local neighborhood, we also find several star-forming regions where new stars are currently being born from collapsing clouds of gas and dust. The nearest major star-forming region is the Taurus Molecular Cloud, located about 450 light-years away. In this region, we can observe the entire process of star formation, from the initial collapse of gas clouds to the emergence of young stars surrounded by planetary disks, where new solar systems may be forming. Another nearby star-forming region is the Orion Nebula, visible to the naked eye as the middle star in Orion's sword. Located about 1,300 light-years away, the Orion Nebula is a stellar nursery where hundreds of new stars have formed within the last few million years. The intense radiation from these young, hot stars illuminates the surrounding gas clouds, creating one of the most spectacular sights in the night sky. The study of these nearby star-forming regions has revolutionized our understanding of how planetary systems form. Observations with powerful telescopes have revealed planetary disks around many young stars, providing direct evidence that planet formation is a common process throughout the galaxy. Some of these disks show gaps and rings that may indicate planets are already forming within them, giving us glimpses of solar systems in their earliest stages of development. Our local neighborhood also contains several brown dwarfs, objects that are too small to sustain nuclear fusion like true stars, but too large to be considered planets. These failed stars, sometimes called stellar embryos, represent an intermediate class of objects between the largest planets and the smallest stars. Brown dwarfs are difficult to detect because they emit very little light, but infrared surveys have revealed that they are relatively common in our galactic neighborhood. The nearest known brown dwarf to Earth is Lumen 16, a binary system located just 6.5 light-years away. This system consists of two brown dwarf objects orbiting each other, each with a mass roughly 3% that of our Sun. Despite being so close to Earth, Lumen 16 is far too faint to see with the naked eye, and was only discovered in 2013. As we map the three-dimensional structure of our local neighborhood, we find that stars are not distributed randomly through space. Instead, they show patterns and groupings that reflect their common origins and the dynamics of galactic rotation. Many nearby stars form together in stellar associations and are still moving through space as loose groups, gradually dispersing over millions of years. One such stellar association is the Ursa Major Moving Group, which includes 5 of the 7 bright stars in the Big Dipper constellation. These stars, along with dozens of others scattered across the sky, all share similar motions through space and likely formed together in the same star-forming region about 300 million years ago. Over time, the group has spread out due to galactic rotation and gravitational perturbations, but the stars still retain evidence of their common origin. The mapping of stellar motions in our local neighborhood has also revealed streams of stars that were likely ejected from globular clusters or disrupted by gravitational interactions with massive objects. These stellar streams provide clues about the gravitational structure of our galaxy and the distribution of dark matter in our cosmic vicinity. Recent surveys using the Gaia Space Telescope have measured the precise positions and motions of over 1 billion stars, including virtually every star visible in our local neighborhood. This unprecedented dataset has revealed complex patterns of stellar motion that were previously hidden, including evidence for past close encounters between our solar system and other stars. These stellar encounters, while rare, can have significant effects on the outer regions of our solar system. Computer simulations suggest that a close stellar flyby could disrupt the Oort cloud, sending a shower of comets toward the inner solar system. Some astronomers have proposed that such encounters might be responsible for mass extinction events in Earth's history, though this connection remains speculative. The boundaries of our local neighborhood are not sharply defined but gradually merge into the larger galactic environment. As we look outward to distances of hundreds of light-years, we begin to see the larger scale structure of our spiral arm of the Milky Way galaxy. Our local neighborhood is part of what astronomers call the Orion Arm, or local arm, a minor spiral arm located between 2 major spiral arms of our galaxy. The Orion Arm extends for thousands of light-years and contains millions of stars, along with numerous star-forming regions, supernova remnants, and other astronomical objects. Our Sun and its neighbors are located roughly in the middle of this spiral arm, about 26,000 light-years from the center of the Milky Way galaxy. Understanding our place within this larger galactic structure helps put our local neighborhood in perspective. While our nearby stellar environment might seem vast and sparsely populated, it represents just a tiny sample of the hundreds of billions of stars that populate our galaxy. Each of those distant stars likely has its own local neighborhood, potentially filled with planets, moons, and perhaps even life. The exploration of our local neighborhood continues to reveal new discoveries and surprises. As our observational capabilities improve, we find more brown dwarfs, more planetary systems, and more complex structures in the nearby interstellar medium. Future space missions will provide even more detailed maps of our cosmic vicinity, helping us understand how our solar system formed and evolved within this larger galactic context. Advanced telescopes and space missions are beginning to study the atmospheres of planets around nearby stars, searching for signs of habitability or even life itself. The James Webb Space Telescope can analyze the atmospheres of planets orbiting stars within a few dozen light-years of Earth, potentially detecting water vapor, oxygen, or other molecules that might indicate the presence of life. As we conclude our tour of our local neighborhood, we are left with a profound appreciation for the vast scales involved, even in our immediate cosmic vicinity. The region of space we have explored, extending out to perhaps 50 light-years from Earth, contains enough wonders to occupy astronomers for centuries. Yet this entire neighborhood, vast as it seems, represents less than 1% of our galaxy. Beyond our local neighborhood lies a galaxy containing hundreds of billions of stars, vast spiral arms stretching across tens of thousands of light-years, and a central region harboring mysteries we are only beginning to understand. Our journey outward has only just begun, and the scales we will encounter as we venture deeper into the cosmos will challenge our ability to comprehend the true vastness of the universe we inhabit. As we venture beyond our local stellar neighborhood, we encounter a structure so vast and magnificent that it challenges our ability to comprehend its true scale. We call it the Milky Way, that faint band of light stretching across our night sky, but this understated name barely hints at the cosmic leviathan that is our home galaxy. The Milky Way is not just a collection of stars, it is an entire universe unto itself, containing hundreds of billions of suns, countless planets, vast clouds of gas and dust, and mysteries that continue to astound astronomers. The name Milky Way comes from ancient mythology, where various cultures saw the pale band across the sky as spilled milk from the gods, or a pathway for spirits. The Romans called it Via Lactea, the road of milk, while other cultures saw it as a river of stars, or the backbone of the night sky. None of these ancient observers could have imagined that this ghostly light represents our view from within a vast galaxy containing more stars than there are grains of sand on all the beaches of Earth. To understand the Milky Way, we must first grasp the mind-boggling scales involved. Our galaxy spans approximately 100,000 light-years from edge to edge, making it roughly 25 times larger than our local neighborhood. If our local stellar vicinity were the size of a city block, the Milky Way would cover an area larger than the entire state of Texas. This vast disk of stars rotates majestically through space, completing one full rotation every 225 million years. The sheer size of our galaxy becomes even more staggering when we consider what 100,000 light-years actually means. Light, traveling at over 600 million miles per hour, would take 100,000 years to cross from one edge of the Milky Way to the other. If you could somehow travel at the speed of light, a journey across our galaxy would span a period longer than all of recorded human history. At more realistic speeds achievable by our current spacecraft, the journey would take billions of years, far longer than the current age of the universe. The structure of the Milky Way resembles a cosmic pinwheel, with elegant spiral arms sweeping outward from a central bulge. When viewed from above, our galaxy would appear as a magnificent spiral, with arms trailing behind as the galaxy rotates. These spiral arms are not solid structures but rather density waves, regions where stars and gas clouds are compressed and where new star formation is triggered. As our solar system orbits the galactic center, we occasionally pass through these spiral arms, spending tens of millions of years within their star-forming regions before emerging into the quieter spaces between arms. The spiral pattern itself is a dynamic, ever-changing phenomenon. Unlike the rigid spokes of a wheel, the spiral arms are waves of compression that propagate around the galaxy at a different speed than the stars themselves. Stars drift in and out of the spiral arms over millions of years, experiencing periods of intense radiation and stellar winds when they pass through star-forming regions, followed by quieter intervals in the spaces between arms. Our Sun currently resides about 26,000 light-years from the galactic center, roughly halfway out from the core to the edge. This location places us in what astronomers call the galactic habitable zone, a region where conditions are favorable for the development of complex life. Closer to the galactic center, intense radiation and gravitational disruptions from massive stars and black holes would make planetary systems unstable. The increased frequency of supernovae near the galactic center would bombard nearby planets with lethal radiation, while gravitational perturbations from passing stars could disrupt planetary orbits. Farther out toward the galactic edge, there are fewer heavy elements necessary for planet formation and life as we know it. The metallicity, or abundance of elements heavier than hydrogen and helium, decreases with distance from the galactic center, Rocky planets like Earth require substantial amounts of silicon, iron, magnesium, and other heavy elements that are produced inside massive stars and distributed through supernova explosions. Our location in the galaxy provides an optimal balance of heavy element abundance and relative safety from cosmic catastrophes. The heart of the Milky Way harbors one of the most extreme objects in the known universe, a supermassive black hole called Sagittarius A star. This cosmic monster contains the mass of over 4 million suns compressed into a region smaller than our solar system. To put this incredible density in perspective, if Earth were compressed to the same density as this black hole, our entire planet would be smaller than a marble. Despite its enormous mass, Sagittarius A star is invisible to ordinary telescopes because no light can escape from within its event horizon. We detect its presence only through its gravitational effects on nearby stars, which orbit the black hole at speeds reaching thousands of miles per second. Some of these stars complete their orbits in just 16 years, traveling at velocities that reach nearly 5% the speed of light at their closest approach to the black hole. The recent Event Horizon Telescope project has captured the first direct image of the shadow cast by Sagittarius A star, revealing the glowing disk of superheated material spiraling into the black hole. This achievement represents one of the most remarkable technological accomplishments in astronomy, requiring telescopes around the world to work together as a single instrument the size of our planet. The image shows a dark central region surrounded by a bright ring of gas heated to billions of degrees as it falls toward the black hole. The environment around Sagittarius A star is one of the most extreme in the known universe. Gas falling into the black hole reaches temperatures of millions of degrees and velocities, approaching the speed of light. Magnetic fields thousands of times stronger than Earth's magnetic field twist and contort the plasma into complex structures. Occasionally, the black hole becomes more active, flaring with increased brightness as larger amounts of material fall past the event horizon. Surrounding the central black hole lies the galactic bulge, a roughly spherical region containing older, redder stars that formed during the galaxy's youth over 10 billion years ago. These ancient stars preserve chemical signatures from the early universe, when hydrogen and helium were virtually the only elements available for star formation. Studying these stellar fossils helps astronomers understand how galaxies like ours formed and evolved over cosmic time. The bulge contains roughly 20 billion stars packed into a relatively small volume, creating a stellar density thousands of times greater than in our local neighborhood. If Earth were located in the galactic bulge, our night sky would be filled with thousands of stars brighter than Venus, creating a perpetual twilight that would make the Milky Way's spiral structure clearly visible to the naked eye. The disk of the Milky Way contains most of the galaxy's star-forming activity and younger stellar populations. This is where we find the spectacular spiral arms, glowing with the light of massive blue stars and colorful nebulae. The disk itself is remarkably thin compared to the galaxy's overall size, with a thickness of only about 1,000 light-years. If the Milky Way were scaled down to the size of a dinner plate, the disk would be thinner than a sheet of paper. The spiral pattern is maintained by density waves that propagate around the galaxy, compressing gas clouds and triggering bursts of star formation as they pass. These density waves can be thought of as traffic jams in the galactic disk, where stars and gas clouds pile up temporarily before continuing on their orbits. The compression creates ideal conditions for star formation, which is why the spiral arms appear so bright and colorful in images of other galaxies. The most prominent spiral arms of the Milky Way have been mapped through observations of young, luminous stars and hydrogen gas clouds. The Perseus arm, located outside our orbit, contains some of the most active star-forming regions in the galaxy. This arm stretches for thousands of light-years and contains massive star-forming complexes that can be detected across vast distances. The Sagittarius arm, inside our orbit, harbors numerous stellar nurseries where new generations of stars are currently being born. Our own Orion arm, sometimes called the local arm, is a smaller spiral feature that branches off from the major arms. This minor arm is about 10,000 light-years long and perhaps 3,000 light-years wide, making it a relatively small structure within the galaxy's overall spiral pattern. Despite its modest size compared to the major arms, the Orion arm contains a rich variety of stellar populations and star-forming regions. These spiral arms are not permanent fixtures, but rather transient patterns that form and dissipate over hundreds of millions of years. The current spiral structure of the Milky Way may have been shaped by gravitational interactions with nearby galaxies or by the passage of smaller galaxies through our disk. Computer simulations suggest that spiral patterns are constantly evolving, with arms forming, merging, and breaking apart in an ongoing cosmic dance. The spiral arms also show interesting substructure, with spurs and branches extending between the major arms. Some astronomers suggest that these features result from stellar feedback, where massive stars and supernovae create expanding bubbles of hot gas that can trigger new star formation or disrupt existing structures. The complex interplay between stellar winds, supernova explosions, and galactic rotation creates an ever-changing tapestry of structure within the galactic disk. Between the spiral arms lie vast regions of space containing older stars and less active star formation. These inter-arm regions, while less spectacular than the spiral arms themselves, contain the majority of the galaxy's stellar mass. Here we find a mix of stellar populations representing different epochs in the galaxy's history, from ancient red giants that have exhausted their nuclear fuel to middle-aged stars like our Sun. The stellar populations of the Milky Way tell a story of chemical evolution spanning billions of years. The oldest stars in our galaxy contain almost no elements heavier than hydrogen and helium, reflecting the composition of the early universe when the first stars formed from pristine primordial gas. These population 2 stars, found primarily in the galactic halo and bulge, have metallicities less than 1% that of our Sun. As successive generations of massive stars lived and died, they enriched the interstellar medium with heavier elements created in their nuclear cores and explosive deaths. Stellar nucleosynthesis, the process by which stars fuse lighter elements into heavier ones, gradually increased the abundance of carbon, oxygen, silicon, iron, and other elements essential for planet formation. Today's population I stars, including our Sun, are enriched with these stellar products, containing the heavy elements necessary for terrestrial planets and life. This process of stellar nucleosynthesis has gradually increased the metallicity of our galaxy over time. The metallicity gradient across the Milky Way provides clues about how our galaxy formed, with the inner regions showing higher metallicity due to more intense star formation activity and shorter mixing timescales. The outer regions of the galaxy show lower metallicity, reflecting their slower chemical evolution and greater distance from the sites of heavy element production. The study of stellar abundances has revealed that different elements are produced by different types of stars and stellar processes. Elements like carbon and oxygen are primarily produced in the cores of massive stars, while iron peak elements are synthesized during supernova explosions. Neutron capture elements like gold and platinum are thought to be produced during the collision of neutron stars, events so rare that they may occur only once every 10,000 years in a galaxy like ours. The Milky Way contains an estimated 200 to 400 billion stars, though this number remains uncertain due to the difficulty of counting stars throughout the entire galaxy. The vast majority of these stars are red dwarfs, small, cool stars that burn their nuclear fuel slowly and can shine for trillions of years. These diminutive stars, with masses less than half that of our Sun, make up roughly 75% of all stars in the galaxy. Our Sun, a yellow dwarf star, is actually larger and more luminous than about 90% of all stars in the galaxy. Stars more massive than our Sun become increasingly rare, with the most massive stars containing 50 to 100 times the Sun's mass. These stellar giants burn through their nuclear fuel in just a few million years, living fast and dying young in spectacular supernova explosions. Among these hundreds of billions of stars, astronomers estimate that tens of billions may host planetary systems. The Kepler Space Telescope and other planet hunting missions have revealed that planetary systems are extremely common, with many stars hosting multiple planets. Statistical analysis of Kepler data suggests that virtually every star in the galaxy hosts at least one planet, making planetary systems the rule rather than the exception. Some of these exoplanets orbit within their star's habitable zone, where liquid water could potentially exist on their surfaces. Current estimates suggest that our galaxy may contain 10 to 40 billion potentially habitable planets, though the actual number that could support life as we know it remains highly uncertain. Factors such as atmospheric composition, magnetic field strength, and stellar activity all play crucial roles in determining planetary habitability. The search for potentially habitable worlds has identified thousands of exoplanet candidates within our galaxy. Some of these worlds are remarkably Earth-like, orbiting Sun-like stars at distances that could allow for moderate surface temperatures. Kepler 452b, for example, orbits a star very similar to our Sun at a distance that places it squarely within the habitable zone. This planet receives only 10% more energy from its star than Earth receives from the Sun. Others orbit red dwarf stars, which are much more common than Sun-like stars, but present unique challenges for habitability due to their tendency to produce powerful stellar flares. Red dwarf stars can remain stable for trillions of years, far longer than the current age of the universe, but their planets must orbit very close to receive sufficient energy for liquid water. This close proximity exposes them to intense stellar radiation and strong tidal forces that could strip away their atmospheres. Beyond individual stars and their planetary systems, the Milky Way contains vast clouds of gas and dust that serve as the raw material for future star formation. These molecular clouds can span hundreds of light years and contain enough material to form thousands of new stars. The largest molecular clouds in our galaxy contain millions of times the mass of our Sun, making them among the most massive objects in the Milky Way. The molecular clouds exist primarily in the cold, dense regions of the galactic disk, where temperatures drop to just a few degrees above absolute zero. In these frigid environments, hydrogen atoms combine to form molecular hydrogen, while heavier elements freeze onto tiny dust grains. Carbon monoxide, water, ammonia, and dozens of other molecules have been detected in these clouds, creating a complex chemistry that may be relevant to the origins of life. The most famous of these star-forming regions include the Orion Nebula, the Eagle Nebula, and the Carina Nebula, each a cosmic nursery where new stars are currently being born. These regions glow with the light of young, hot stars that ionize the surrounding gas, creating spectacular displays of colored light, visible across thousands of light years. The intricate structures within these nebulae, shaped by stellar winds and radiation pressure, reveal the complex processes involved in star formation. The Orion Nebula, located about 1,300 light-years from Earth, is one of the most studied star-forming regions in the galaxy. This stellar nursery spans about 24 light-years and contains about 2,000 times the mass of our Sun in gas and dust. Within this cloud, hundreds of new stars have formed within the last few million years, with many more still in the process of formation. The brightest stars in the Orion Nebula are massive, hot stars that will live for only a few million years before exploding as supernovae. These stellar giants produce intense ultraviolet radiation that ionizes the surrounding hydrogen gas, causing it to glow with the characteristic red light of hydrogen emission. The complex structure of the nebula, with its intricate filaments and cavities, results from the interplay between stellar winds, radiation pressure, and the turbulent motions of the gas. Stellar death also plays a crucial role in shaping the Milky Way's structure and evolution. When massive stars exhaust their nuclear fuel, they explode as supernovae, releasing enormous amounts of energy and heavy elements into the surrounding space. These explosions create expanding shock waves that can trigger new star formation in nearby molecular clouds, while also heating and dispersing gas over vast regions. A single supernova explosion releases more energy in a few seconds than our Sun will produce over its entire 10 billion-year lifetime. The shock wave from the explosion can heat gas to temperatures of millions of degrees and accelerate particles to nearly the speed of light. These cosmic ray particles continue to permeate the galaxy long after the initial explosion, contributing to the background radiation environment throughout the Milky Way. The remnants of supernova explosions, called supernova remnants, can be detected throughout the galaxy as expanding shells of hot, glowing gas. These structures can persist for tens of thousands of years, gradually slowing down as they sweep up more and more interstellar material. Some of the most spectacular examples include the Crab Nebula, the remnant of a supernova observed by Chinese astronomers in the year 1054, and Cassiopeia A, the remnant of a more recent explosion that occurred about 300 years ago. The Crab Nebula represents one of the most intensively studied objects in astronomy. The supernova that created this nebula was so bright that it was visible during daylight for over 3 weeks, appearing brighter than Venus in the night sky. Today, the nebula continues to expand at over 3 million miles per hour, driven by energy from the pulsar at its center. This pulsar, the collapsed core of the original star, spins 30 times per second while emitting beams of radiation that sweep across space like a cosmic lighthouse. Supernovae also leave behind exotic stellar remnants that represent some of the most extreme objects in the universe. Neutron stars, formed when a star's core collapses to incredible density, contain more mass than our Sun compressed into a sphere only about 12 miles across. A teaspoon of neutron star material would weigh as much as Mount Everest, and the gravitational field at the surface is so strong that an object would hit the neutron star at nearly half the speed of light if dropped from just 1 meter above the surface. Some neutron stars spin rapidly while emitting beams of radiation, creating pulsars that sweep across space like cosmic lighthouses. The fastest known pulsar spins over 700 times per second, faster than a kitchen blender. These incredibly precise cosmic clocks keep better time than the most accurate atomic clocks on Earth, losing less than 1 second over millions of years. The most massive stellar remnants become black holes, regions of space where gravity is so strong that nothing, not even light, can escape. While stellar mass black holes are much smaller than the supermassive black hole at our galaxy's center, they still represent some of the most extreme environments in the universe. Recent gravitational wave detectors have revealed that black hole mergers are relatively common events, producing ripples in space-time that can be detected across vast cosmic distances. The LIGO and Virgo gravitational wave observatories have detected dozens of black hole mergers within our cosmic neighborhood, revealing a population of black holes more numerous than previously expected. These collisions occur when two black holes spiral into each other, releasing in their final moments more energy in gravitational waves than all the stars in the observable universe emit in light. The Milky Way's structure extends far beyond the visible disk of stars. Surrounding our galaxy is an enormous spherical halo containing globular clusters, ancient streams of stars, and vast amounts of dark matter. The globular clusters are compact collections of hundreds of thousands of very old stars, some of the first objects to form in our galaxy over 12 billion years ago. These globular clusters represent stellar systems unlike anything found in the galactic disk. Each cluster contains stars packed thousands of times more densely than in our local neighborhood, creating environments where stellar collisions and interactions are common. The central regions of globular clusters may contain intermediate mass black holes, formed through the merger of smaller stellar remnants over billions of years. The globular clusters orbit the galactic center in highly elliptical paths that take them far above and below the galactic disk. Their orbits provide clues about the total mass and structure of our galaxy, including the distribution of dark matter that makes up the majority of the Milky Way's mass. Although we cannot directly observe dark matter, its gravitational effects are essential for holding our galaxy together and maintaining the observed rotation speeds of stars in the outer regions. The dark matter halo of the Milky Way extends to distances of several 100,000 light-years, far beyond the visible edge of the stellar disk. This invisible component contains roughly 5 times more mass than all the visible stars, gas, and dust in our galaxy combined. The nature of dark matter remains one of the greatest mysteries in modern physics, with candidates ranging from exotic subatomic particles to primordial black holes formed in the early universe. Understanding the nature and distribution of dark matter remains one of the greatest challenges in modern astronomy and physics. Direct detection experiments deep underground search for dark matter particles interacting with ordinary matter, while space-based telescopes map the gravitational effects of dark matter on visible structures. The distribution of dark matter may hold the key to understanding how galaxies form and evolve over cosmic time. Within this dark matter halo, astronomers have discovered numerous stellar streams, long trails of stars that were torn from smaller galaxies or globular clusters by the Milky Way's gravitational forces. These streams provide evidence that our galaxy has grown over time by absorbing smaller, neighboring galaxies, a process that continues today. The largest known stellar stream, called the Sagittarius Stream, wraps around our entire galaxy and represents the ongoing disruption of a small galaxy that is being torn apart by the Milky Way's gravity. The Sagittarius dwarf galaxy, the source of this stream, originally contained several billion stars, but has been gradually stripped apart over billions of years as it orbits through the Milky Way's halo. The tidal forces from our galaxy's gravity have pulled stars from the dwarf galaxy, creating a stream that extends completely around the sky. This process of galactic cannibalism has likely added hundreds of millions of stars to the Milky Way's halo over cosmic time. The process of galactic cannibalism has played a major role in shaping the Milky Way's current structure. Computer simulations suggest that our galaxy has absorbed dozens of smaller galaxies over its lifetime, incorporating their stars into the galactic halo and disk. This ongoing accretion process continues today, with several small galaxies currently in the process of being disrupted and absorbed. Evidence for past merger events can be found throughout the galaxy's stellar populations. Chemical abundance patterns in halo stars reveal signatures of different star formation environments, suggesting that these stars originated in smaller galaxies that were later absorbed by the Milky Way. The Gaia Space Telescope has revealed numerous stellar streams and substructures in the galactic halo, each telling a story of cosmic collision and accretion. One of the most significant future events in the Milky Way's evolution will be its collision with the Andromeda Galaxy, our nearest large galactic neighbor. Located about 2.5 million light-years away, Andromeda is currently approaching us at about 250,000 miles per hour. Astronomers predict that the two galaxies will begin to interact gravitationally in about 4.5 billion years, ultimately merging into a single, larger galaxy. This galactic collision, while dramatic on cosmic scales, will likely have minimal direct impact on individual star systems. The vast distances between stars mean that actual stellar collisions will be extremely rare. Instead, the gravitational interaction will dramatically reshape both galaxies, potentially triggering bursts of star formation and altering the orbits of countless stars. Our solar system will likely survive the merger, though it may be flung into a very different part of the combined galaxy. Computer simulations of the Milky Way Andromeda collision suggest that the merger will create a large elliptical galaxy, temporarily nicknamed Milkomeda. This new galaxy will be significantly larger than either of its parent galaxies, with a total stellar mass exceeding 1 trillion solar masses. The merger process will take several billion years to complete, with multiple close passes before the two galactic cores finally merge. Recent observations have revealed that the Milky Way is part of a larger structure called the Local Group, which includes Andromeda, dozens of smaller galaxies, and the vast empty spaces between them. The gravitational dance between these galaxies influences their individual evolution and will ultimately determine their collective fate over cosmic time. The study of our galaxy continues to reveal new complexities and surprises. Advanced surveys using space-based telescopes have mapped the three-dimensional structure of the Milky Way with unprecedented precision, revealing warps, ripples, and other deviations from a simple spiral disk. These features provide clues about past interactions with other galaxies and the ongoing effects of dark matter substructures. The galactic disk shows a pronounced warp in its outer regions, with the disk bending upward on one side and downward on the other. This warping may result from gravitational interactions with the Large and Small Magellanic Clouds, two satellite galaxies that orbit the Milky Way. As these smaller galaxies orbit through the galactic halo, their gravitational influence can distort the outer regions of the disk. Recent discoveries have also revealed that the Milky Way is larger than previously thought, with the stellar disk extending farther from the galactic center than earlier estimates suggested. New observations have pushed the edge of the disk out to nearly 60,000 light-years from the center, making our galaxy about 20% larger than previously believed. The chemical composition of stars throughout the galaxy tells a detailed story of stellar evolution and nucleosynthesis. By analyzing the light from millions of stars, astronomers can trace how different elements have been produced and distributed throughout the galaxy over billions of years. This galactic archaeology reveals the complex history of star formation, stellar death, and chemical mixing that has shaped the Milky Way into its current form. Large-scale surveys like the Sloan Digital Sky Survey and the Gaia mission have revolutionized our understanding of galactic structure and evolution. These projects have measured the positions, motions, and chemical compositions of millions of stars, creating detailed maps of stellar populations throughout the galaxy. The data reveal complex patterns of stellar motion that preserve signatures of past merger events and ongoing dynamical processes. Modern technology has also enabled the detection of gravitational waves from colliding black holes and neutron stars within our galaxy and beyond. These observations provide new insights into the most extreme events in the universe and help astronomers understand the population and behavior of compact objects throughout the Milky Way. The The search for life within our galaxy remains one of the most compelling areas of astronomical research. With billions of potentially habitable planets scattered throughout the Milky Way, the possibility that life has arisen elsewhere seems increasingly likely. Radio telescopes scan the galaxy for artificial signals, while other instruments search for biosignatures in the atmospheres of nearby exoplanets. The search for extraterrestrial intelligence continues to monitor millions of stars for signs of technological civilizations. While no confirmed signals have been detected, the search has placed important constraints on the prevalence of radio-transmitting civilizations in our galactic neighborhood. Future surveys with more sensitive instruments will extend this search to encompass larger volumes of the galaxy. Future missions will extend our ability to study the galaxy in unprecedented detail. The James Webb Space Telescope can observe individual stars in the most distant parts of the Milky Way, while upcoming extremely large telescopes will be able to directly image and analyze the atmospheres of Earth-sized planets around nearby stars. Space-based missions may eventually provide detailed maps of stellar motions, chemical compositions, and planetary systems throughout our entire galactic neighborhood. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct a comprehensive survey of the galactic bulge, monitoring hundreds of millions of stars for signs of planetary transits and gravitational microlensing events. This mission could discover thousands of new exoplanets and provide crucial data about the frequency of Earth-like worlds throughout the galaxy. As we conclude our exploration of the Milky Way, we are left with a profound sense of our place within this vast cosmic structure. Our entire solar system, with all its planets, moons, and the countless smaller bodies that inhabit the space around our sun, represents less than a grain of sand compared to the immense scale of our galaxy. Yet we are intimately connected to this larger structure, formed from materials created in the nuclear furnaces of previous generations of stars, and shaped by the same gravitational forces that maintain the galaxy's spiral pattern. The Milky Way is more than just our cosmic address. It is the stage upon which the entire drama of stellar evolution plays out, from the birth of new stars in glowing nebulae to the spectacular deaths of massive stars in supernova explosions. It is a vast recycling system that transforms hydrogen and helium into all the heavier elements necessary for planets and life. It is a gravitational anchor that holds together hundreds of billions of star systems while participating in an even grander cosmic dance with neighboring galaxies. Understanding our galaxy provides crucial context for the next phase of our journey outward. As vast as the Milky Way appears, it is but one galaxy among billions scattered throughout the observable universe. Beyond our galactic boundaries lies a cosmos populated with galaxies of every size and type, from small, irregular collections of stars to massive elliptical galaxies containing trillions of suns. Our journey into these even greater scales will reveal structures and distances that make even our enormous galaxy seem small by comparison. As we step beyond the boundaries of our home galaxy, we enter a realm where distances become so vast that even the Milky Way, with its 100 billion stars and 100,000 light-year span, begins to seem small. Here we encounter our nearest galactic neighbors, bound together by gravity into a cosmic community known as the Local Group. This collection of galaxies represents our immediate cosmic neighborhood, a gravitationally bound cluster spanning roughly 10 million light-years across. The Local Group contains over 80 known galaxies, though this number continues to grow as astronomers discover new, faint dwarf galaxies hidden in the outskirts of our cosmic neighborhood. The group is dominated by three large spiral galaxies: our own Milky Way, the magnificent Andromeda Galaxy, and the smaller, but still substantial Triangulum Galaxy. These three giants contain the vast majority of the Local Group's total mass and stellar population, while dozens of smaller satellite galaxies orbit around them like cosmic moons. The Andromeda Galaxy, also known as Messier 31, stands as the Local Group's largest member and our nearest major galactic neighbor. Located approximately 2.5 million light-years from Earth, Andromeda contains roughly 1 trillion stars, making it perhaps twice as massive as our own Milky Way. This cosmic giant spans about 220,000 light-years from edge to edge, making it more than twice the diameter of our home galaxy. When we observe Andromeda in our night sky, we are looking at light that left the galaxy 2.5 million years ago, when our earliest human ancestors were just beginning to use stone tools. The photons reaching our eyes tonight began their journey across the cosmic void long before modern humans existed, carrying with them images of stellar births and deaths that occurred in an unimaginably distant realm of space. Andromeda's spiral structure displays a beauty and complexity that rivals our own galaxy. The galaxy possesses a prominent central bulge surrounded by well-defined spiral arms containing active star-forming regions. Unlike the Milky Way, Andromeda shows evidence of a double nucleus at its core, possibly the result of a past galactic merger that left behind two supermassive black holes orbiting each other at the galaxy's heart. The galaxy's spiral arms stretch outward for tens of thousands of light-years, traced by brilliant blue stars and glowing nebulae where new stellar generations are being born. Observations with powerful telescopes reveal individual star-forming regions within Andromeda's disk, each containing enough raw material to create thousands of new stars. Some of these regions are larger and more active than any found in our own galaxy, suggesting that Andromeda may be experiencing a more vigorous period of star formation. Andromeda is approaching our galaxy at approximately 250,000 miles per hour, a speed that seems tremendous by earthly standards but represents only a tiny fraction of the speed of light. At this rate, it would take the galaxy over 10 billion years to cross the distance currently separating us, but gravitational attraction is accelerating this approach. Astronomers predict that the two galaxies will begin to interact gravitationally in about 4.5 billion years, ultimately merging into a single, massive, elliptical galaxy. The third major member of the local group is the Triangulum Galaxy, also known as Messier 33. Located about 3 million light-years from Earth, Triangulum is significantly smaller than either the Milky Way or Andromeda, containing perhaps 40 billion stars. Despite its smaller size, Triangulum displays active star formation and a well-defined spiral structure that makes it one of the most photogenic galaxies in our cosmic neighborhood. Triangulum's spiral arms are particularly rich in young, blue stars and hydrogen gas clouds, indicating ongoing star formation throughout much of the galaxy's disk. The galaxy lacks a prominent central bulge, giving it a more open, face-on appearance that allows astronomers to study its spiral structure in detail. Some regions within Triangulum show star formation rates higher than those found in most parts of the Milky Way, suggesting that this smaller galaxy may be more dynamically active than its larger neighbors. The gravitational relationship between these three large galaxies shapes the entire local group. Computer simulations suggest that all three galaxies are slowly falling toward their common center of mass, engaged in a complex gravitational dance that will ultimately lead to a series of mergers over the next several billion years. The Triangulum Galaxy may be the first to merge with the Andromeda Milky Way system, adding its stars to an already massive combined galaxy. Surrounding these three galactic giants are dozens of smaller satellite galaxies, ranging from relatively substantial dwarf galaxies to tiny collections of stars barely distinguishable from large globular clusters. These satellite galaxies provide crucial insights into galaxy formation and evolution, as many of them preserve conditions and stellar populations representative of the early universe. The most prominent satellite galaxies of the Milky Way are the Large and Small Magellanic Clouds, two irregular galaxies visible to the naked eye from the southern hemisphere. The Large Magellanic Cloud, located about 160,000 light-years away, contains roughly 10 billion stars and displays active star formation in regions like the spectacular Tarantula Nebula. This enormous star-forming complex is so bright that if it were located as close as the Orion Nebula, it would cast shadows on Earth. The Small Magellanic Cloud, slightly more distant at about 200,000 light-years, contains about 3 billion stars and shows evidence of recent gravitational interactions with its larger companion. Both Magellanic Clouds are connected to our galaxy by streams of hydrogen gas, suggesting that they are being gradually disrupted by the Milky Way's gravitational field. These galaxies may eventually be absorbed entirely into our galaxy, adding their stars to the Milky Way's halo. Recent discoveries have revealed that the local group contains many more dwarf galaxies than previously known. Advanced surveys using sensitive telescopes have identified dozens of ultra-faint dwarf galaxies orbiting the major galaxies, some containing fewer than 1,000 stars total. These tiny galaxies are so faint that they were undetectable until recently, yet they may represent the most common type of galaxy in the universe. These ultra-faint dwarfs provide important tests of our understanding of dark matter and galaxy formation. Many of these galaxies appear to be dominated by dark matter, with mass-to-light ratios hundreds of times larger than typical galaxies. Some contain so few stars that they are barely distinguishable from dark matter halos, with a small amount of ordinary matter mixed in, representing the smallest galaxies known to exist. The study of local group galaxies has revolutionized our understanding of how galaxies form and evolve over cosmic time. Unlike distant galaxies, which appear as they were billions of years ago due to light travel time, local group members can be studied in their current state with extraordinary detail. Individual stars can be resolved and studied in even the most distant local group galaxies, allowing astronomers to trace stellar populations and chemical evolution with unprecedented precision. Observations of local group galaxies have revealed that galaxy formation is a complex, ongoing process rather than a single event in the distant past. Many dwarf galaxies show evidence of multiple episodes of star formation, separated by long periods of quiescence. Some appear to have had their star formation triggered by gravitational interactions with larger galaxies, while others show signs of having their gas supplies stripped away by these same interactions. The local group itself exists within an even larger structure known as the Virgo supercluster, also called the local supercluster. This enormous collection of galaxy groups and clusters spans roughly 100 million light-years and contains thousands of galaxies organized into filaments, sheets, and voids. The local group represents just one small component of this vast cosmic web, located on the outskirts of the supercluster's main concentration of matter. At the heart of the Virgo supercluster lies the Virgo cluster, a massive collection of over 1,300 galaxies, located about 54 million light-years from Earth. This cluster contains some of the largest and most massive galaxies known, including the giant elliptical galaxy Messier 87, which harbors a supermassive black hole with a mass equivalent to 6.5 billion suns. The cluster's gravitational influence extends throughout the supercluster, slowly drawing in surrounding galaxy groups, including our own local group. The Virgo cluster represents our first glimpse into the realm of rich galaxy clusters, dense concentrations of hundreds or thousands of galaxies bound together by gravity. These clusters are among the largest gravitationally bound structures in the universe, with total masses often exceeding that of 1,000 trillion suns. The space between cluster galaxies is filled with extremely hot gas, heated to temperatures of tens of millions of degrees by the cluster's enormous gravitational field. Within the Virgo cluster, we observe galaxy types and interactions rarely seen in the local group. Giant elliptical galaxies, formed through the merger of multiple smaller galaxies, dominate the cluster's central regions. These galactic behemoths contain trillions of stars, but show little ongoing star formation, having converted most of their gas into stars during their violent formation process. The hot intracluster gas strips away remaining gas from smaller galaxies, effectively shutting down star formation and creating the smooth, featureless appearance characteristic of elliptical galaxies. The cluster environment also produces spectacular examples of galactic cannibalism, where large galaxies grow by absorbing smaller neighbors. The central galaxy of the Virgo cluster, Messier 87, shows evidence of having consumed dozens of smaller galaxies over cosmic time. Long streams and shells of stars surrounding the galaxy provide fossil evidence of these past merger events, creating a complex three-dimensional structure that extends far beyond the galaxy's main body. Beyond the Virgo cluster, our cosmic neighborhood extends to encompass numerous other galaxy groups and clusters within several hundred million light-years. The Coma cluster, located about 300 million light-years away, contains over 1,000 known galaxies and represents one of the richest galaxy clusters in our cosmic vicinity. This cluster is so massive that its gravity noticeably affects the motions of surrounding galaxies across tens of millions of light-years. The Perseus cluster, about 240 million light-years distant, displays some of the most dramatic examples of galaxy cluster physics. X-ray observations reveal enormous bubbles of hot gas blown out by the supermassive black hole in the cluster's central galaxy, creating cavities hundreds of thousands of light-years across. These bubbles provide energy that prevents the cluster's gas from cooling and forming new stars, demonstrating the powerful influence that supermassive black holes can have on their cosmic environment. As we survey these increasingly distant galaxy clusters, we begin to perceive the large-scale structure of the universe itself. Galaxies are not randomly distributed through space, but instead follow a cosmic web of filaments and sheets separated by vast voids containing few galaxies. This structure reflects the distribution of dark matter on the largest scales, with galaxies forming where dark matter density is highest and avoiding regions where dark matter is sparse. The cosmic web extends as far as we can observe, creating a pattern that resembles a three-dimensional spider web or the foam on a cappuccino. Dense filaments of galaxies stretch across hundreds of millions of light years, connecting rich clusters and forming the backbone of cosmic structure. Between these filaments lie cosmic voids, vast regions of space containing very few galaxies and spanning hundreds of millions of light years across. One of the largest structures in our cosmic neighborhood is the Great Wall, also known as the Coma Wall, a vast sheet of galaxies stretching across 500 million light years. This structure contains thousands of galaxies, arranged in a thin sheet, only about 15 million light years thick, creating one of the largest known structures in the universe. The Great Wall demonstrates that cosmic structure exists on scales comparable to a significant fraction of the observable universe itself. Even larger structures have been discovered in recent decades, including the Sloan Great Wall, which extends over 1 billion light-years across. These enormous structures challenge our understanding of how the universe evolved from the relatively smooth conditions observed in the cosmic microwave background radiation to the complex web of structure we see today. The discovery of such large-scale structures has profound implications for our understanding of cosmic evolution. Computer simulations of structure formation suggest that the cosmic web we observe today grew from tiny density fluctuations in the early universe, amplified over billions of years by gravitational attraction. The largest structures we can observe represent the maximum size of objects that have had time to form since the Big Bang. Beyond several billion light-years, we begin to observe galaxies as they appeared when the universe was significantly younger than it is today. These distant galaxies often appear very different from their modern counterparts, showing higher rates of star formation, more irregular morphologies, and different chemical compositions. By studying galaxies at various distances, astronomers can trace the evolution of cosmic structure over the majority of the universe's history. The most distant galaxy clusters observed lie so far away that we see them as they appeared when the universe was less than half its current age. These early clusters appear to be still in the process of formation, with galaxies falling into the cluster potential for the first time. The hot intracluster gas characteristic of nearby clusters is often absent or much cooler in these distant systems, reflecting their younger evolutionary state. Recent surveys using powerful space-based and ground-based telescopes have mapped the three-dimensional distribution of galaxies across billions of light-years, revealing the cosmic web in unprecedented detail. Projects like the Sloan Digital Sky Survey have measured distances to millions of galaxies, creating detailed maps of structure, extending to distances where the universe was less than half its current age. These surveys have revealed that the basic pattern of the cosmic web, with its filaments, nodes, and voids, extends as far as we can observe. However, the details of this structure evolve over cosmic time, with smaller structures merging to form larger ones in a hierarchical process that continues today. The largest galaxy clusters are still growing through the accretion of smaller groups and individual galaxies. The study of large-scale structure has also provided crucial evidence for the existence of dark energy, the mysterious force that appears to be accelerating the expansion of the universe. Observations of galaxy clustering and the growth of structure over cosmic time show that the expansion of the universe began accelerating about 5 billion years ago, corresponding to the epoch when dark energy began to dominate over matter and dark matter. The nature of dark energy remains one of the greatest mysteries in modern cosmology. Unlike dark matter, which behaves like ordinary matter except that it does not interact electromagnetically, dark energy appears to have properties unlike anything in our everyday experience. Current observations suggest that dark energy makes up about 68% of the total energy density of the universe, yet we have no direct detection of this mysterious component. The search for understanding dark energy has motivated ambitious observational programs designed to map the expansion history of the universe with unprecedented precision. Future surveys will measure the distances to billions of galaxies, tracing how the expansion rate has changed over cosmic time and providing clues about the fundamental nature of dark energy. As we explore ever larger scales and greater distances, we approach the boundaries of the observable universe itself. The most distant galaxies we can observe lie so far away that their light has been traveling toward us for over 13 billion years, showing us these systems as they appeared when the universe was less than 1 billion years old. At these extreme distances, the very concepts of distance and structure begin to take on new meanings. The cosmic web we observe on the largest scales represents the culmination of over 13 billion years of cosmic evolution, from the nearly smooth universe revealed by the cosmic microwave background to the complex tapestry of structure we see today. Each galaxy cluster, each filament of the cosmic web, and each vast cosmic void tells part of the story of how our universe has evolved from its earliest moments to its current state. The local group, vast as it seems from our earthly perspective, represents just one tiny knot in this cosmic web. Our cluster of galaxies, spanning 10 million light-years and containing over 80 individual galaxies, occupies a volume that is minuscule compared to the larger structures that surround us. Yet it is within this small corner of the universe that all of human history has unfolded, and it may be within similar small corners that life has emerged elsewhere in the cosmos. Understanding our place within the local group and the larger cosmic web provides crucial context for appreciating both our cosmic significance and our cosmic insignificance. We are part of structures so vast that light takes millions or billions of years to cross them, yet we are also connected to these structures through the fundamental forces that govern the universe. The same gravity that holds our solar system together also maintains the integrity of galaxy clusters spanning hundreds of millions of light-years. As we prepare to venture even further outward in our cosmic journey, we carry with us an appreciation for the hierarchical nature of cosmic structure. From planets to star systems to galaxy groups to clusters to superclusters, each level of organization reveals new scales of space and time that challenge our imagination. Yet each level is connected to the others through the universal laws of physics that operate consistently across all cosmic scales. The local group and its cosmic neighborhood represent our stepping stone from the familiar realm of individual galaxies to the vast scales of cosmic structure that dominate the universe. Here we learn that galaxies, despite their enormous size, are social creatures that rarely exist in isolation. They cluster together, interact gravitationally, merge and evolve, creating the dynamic, ever-changing cosmic web that fills the universe from the smallest scales to the largest. As our cosmic journey takes us beyond the familiar structures of galaxy clusters and superclusters, we approach one of the most profound concepts in all of astronomy, the observable universe. This represents the ultimate horizon of human knowledge, the farthest boundary we can ever hope to explore with our telescopes and instruments. Beyond this cosmic shore lies a realm forever hidden from our direct observation, a mystery that may contain infinite wonders we can never see. The observable universe is not simply the farthest distance we can currently detect with our most powerful telescopes. Rather, it represents a fundamental limit imposed by the finite age of the universe and the finite speed of light. Since the universe began approximately 13.8 billion years ago, light from the most distant objects has had only that amount of time to reach us. This creates a spherical boundary around Earth, roughly 28 billion light-years in radius, beyond which we can never see, no matter how powerful our instruments become. To truly grasp this concept, imagine sitting by a campfire on a dark night. The light from your fire illuminates everything within a certain radius, creating a sphere of visibility beyond which the darkness remains impenetrable. No matter how bright you make your fire, there will always be regions beyond your light's reach, simply because the light has not had time to travel there and back. The observable universe works on the same principle, but instead of firelight, we are limited by the light from the Big Bang itself and the finite time it has had to reach us. The size of this cosmic horizon might seem contradictory at first glance. If the universe is 13.8 billion years old, why isn't the observable universe simply 13.8 billion light-years in radius? The answer lies in the expansion of space itself. While light from the most distant galaxies has indeed been traveling toward us for nearly the entire age of the universe, those galaxies have been carried away from us by cosmic expansion during the light's journey. The galaxy that emitted the light we see today from the edge of the observable universe is now approximately 46.5 billion light-years away. To understand this cosmic expansion, imagine the universe as the surface of a balloon being inflated. As the balloon expands, points on its surface move away from each other, not because they are traveling through the balloon's surface, but because the surface itself is stretching. Similarly, galaxies move away from us, not by traveling through space, but because space itself is expanding, carrying the galaxies along with it. This expansion is not something galaxies do, but rather something that happens to them. A galaxy at the edge of our observable universe is not racing away from us at tremendous speed through space. Instead, the space between us and that galaxy is constantly growing, like the surface of our balloon analogy. This distinction becomes crucial when we consider that the most distant observable galaxies are receding from us faster than the speed of light, which would be impossible if they were actually moving through space at such velocities. The expansion affects everything we observe in the distant universe. Light from faraway galaxies is stretched as it travels through expanding space, shifting it toward longer, redder wavelengths. This cosmological redshift provides astronomers with a powerful tool for measuring distances to the most remote galaxies, while also revealing the expansion history of the universe itself. The amount of redshift tells us not only how far away a galaxy is, but also how much the universe has expanded since the light left that galaxy. The relationship between redshift and distance is not linear, as it would be in a static universe. Instead, it follows a complex curve that depends on the expansion history of the universe, including the effects of matter, and dark energy. By carefully measuring this relationship using standard candles like Type Ia supernovae, astronomers have been able to map the expansion history of the universe and discover the existence of dark energy. The edge of the observable universe corresponds to a time when the universe was very different from what we see today. The most distant galaxies we can observe appear as they were when the universe was less than 1 billion years old, a time when star formation was much more vigorous and galaxies had dramatically different properties than their modern counterparts. These ancient systems often appear smaller, more irregular, and bluer than nearby galaxies, reflecting their youth and active star-forming nature. These early galaxies were forming in a universe that was much denser than today, with matter and dark matter packed into a smaller volume. The higher density meant that gravitational interactions were stronger and more frequent, leading to rapid galaxy assembly and intense bursts of star formation. Many of these early galaxies were undergoing their first major episodes of star formation, creating massive, hot stars that lived fast and died young in spectacular supernova explosions. The chemical composition of these distant galaxies differs dramatically from modern systems. Early in cosmic history, the universe contained only hydrogen, helium, and trace amounts of lithium produced during Big Bang nucleosynthesis. All heavier elements, from carbon and oxygen to iron and gold, had to be manufactured inside stars and distributed through supernova explosions. The most distant galaxies we observe are still in the process of creating these elements for the first time, showing much lower metallicity than galaxies in our cosmic neighborhood. But even these distant galaxies do not represent the absolute edge of the observable universe. There comes a point in cosmic history when we can no longer see individual galaxies at all, not because our telescopes lack sufficient power, but because galaxies as we know them had not yet formed. Beyond a redshift corresponding to roughly 1 billion years after the Big Bang, we enter an era when the universe was too young for complex structures to have assembled. During this early epoch, matter was still organizing itself under the influence of gravity, with dark matter beginning to collapse into the first halos that would eventually host galaxies. The process of structure formation follows a bottom-up hierarchy, with smaller objects forming first and then merging to create larger structures. The very first stars, known as Population 3 stars, formed within small dark matter halos when the universe was only a few 100 million years old. These primordial stars were unlike any stars we see today. Composed entirely of hydrogen and helium, they could grow to enormous masses, perhaps 100 to 300 times the mass of our Sun. Without heavier elements to help cool their gas clouds during formation, these stars had to be much more massive than modern stars to ignite nuclear fusion. They burned brilliantly but briefly, living only a few million years before exploding as the first supernovae in cosmic history. The death of these first stars began the process of chemical enrichment that would eventually make planets and life possible. Their supernova explosions scattered newly created heavy elements into the surrounding gas, seeding future generations of star formation with the carbon, oxygen, silicon, and iron necessary for rocky planet formation. Some of these massive stars may have collapsed directly into black holes, providing the seeds for the supermassive black holes we observe at the centers of galaxies today. Pushing even further back in time, we encounter the cosmic dark ages, a period lasting several 100 million years, when the universe contained no luminous objects whatsoever. During this epoch, the first stars had not yet formed, and the universe was filled only with clouds of hydrogen and helium gas, slowly collapsing under their own gravity. This period remains largely invisible to our current telescopes, though future instruments may be able to detect the faint radio signals from hydrogen gas during this crucial era. The cosmic dark ages began when the universe became transparent to light for the first time, an event known as recombination that occurred roughly 380,000 years after the Big Bang. Before this moment, the universe was so hot that electrons could not bind to atomic nuclei, creating a plasma that scattered light in all directions. When the universe cooled sufficiently for atoms to form, this cosmic fog lifted, allowing light to travel freely through space for the first time. The end of the Dark Ages came gradually as the first stars began to form, and their intense ultraviolet radiation started to reionize the hydrogen gas around them. This epoch of reionization, occurring roughly 500 million to 1 billion years after the Big Bang, represents one of the most dramatic phase transitions in cosmic history. The universe transformed from a cold, dark, neutral state to a hot, bright, ionized condition that persists today. The ultimate boundary of the observable universe is marked by the cosmic microwave background radiation, a faint afterglow from the Big Bang that permeates all of space. This radiation represents our view of the universe when it was only 380,000 years old, a time when it finally became transparent to light for the first time. Before this moment, the universe was opaque to electromagnetic radiation, making it impossible to see deeper into cosmic history using conventional telescopes. The cosmic microwave background appears remarkably uniform across the sky, varying in temperature by only about 1 part in 100,000. These tiny temperature fluctuations represent the seeds from which all cosmic structure eventually grew. Regions that were slightly denser than average became the sites where galaxies and galaxy clusters would eventually form, while slightly less dense regions became the cosmic voids we observe today. The patterns in these temperature fluctuations encode a wealth of information about the universe's fundamental properties. The size and amplitude of the fluctuations tell us about the amounts of ordinary matter, and dark energy in the universe. The polarization patterns in the radiation provide additional constraints on cosmic inflation and the physics of the early universe. Even the absence of certain patterns provides important information, ruling out alternative theories of cosmic evolution. The study of the cosmic microwave background has revolutionized our understanding of the universe's fundamental properties. Detailed measurements by satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft have determined the universe's age, composition, and geometry with extraordinary precision. These observations reveal that ordinary matter makes up only about 5% of the universe's total energy density, with dark matter contributing about 27% and dark energy accounting for the remaining 68%. The precision of these measurements is truly remarkable. We now know the age of the universe to within about 1%, the density of dark matter to within a few percent, and the overall geometry of space to extraordinary accuracy. The cosmic microwave background has provided the most precise measurements of fundamental cosmological parameters, establishing the standard model of cosmology on a firm observational foundation. The patterns in the cosmic microwave background also provide crucial evidence for the theory of cosmic inflation, which proposes that the universe underwent a period of exponential expansion during its first fraction of a second. This inflation would have stretched tiny quantum fluctuations to cosmic scales, creating the density variations we observe in the microwave background. The remarkably good agreement between inflation theory predictions and observed patterns represents one of the greatest triumphs of theoretical cosmology. Inflation theory makes specific predictions about the statistical properties of cosmic microwave background fluctuations, including their amplitude, scale dependence, and non-Gaussian characteristics. The Planck satellite has measured these properties with extraordinary precision, finding excellent agreement with the simplest inflation models, while ruling out many alternative theories. However, inflation remains an active area of research, with many details still to be understood. Within the observable universe, astronomers have catalogued billions of galaxies, spanning an enormous range of sizes, masses, and morphologies. The largest surveys have detected galaxies out to distances where the universe was less than 10% of its current age, revealing how cosmic structure has evolved over the vast majority of cosmic history. These observations show that galaxy formation began surprisingly early in cosmic history, with some galaxies forming stars when the universe was less than 500 million years old. The Hubble Space Telescope has been instrumental in pushing observations to ever greater distances and earlier cosmic times. Deep field observations, where the telescope stares at tiny patches of seemingly empty sky for hundreds of hours, have revealed thousands of distant galaxies in regions that appeared blank to previous surveys. These observations show that the universe was already rich with galaxies when it was less than 1 billion years old. The most distant confirmed galaxy currently known appears as it was when the universe was only 400 million years old, just 3% of its current age. This ancient system, designated GNZ11, is remarkably compact and blue, indicating vigorous star formation in a galaxy much smaller than the Milky Way. The discovery of such early galaxies has forced astronomers to revise their models of how quickly cosmic structure could assemble in the young universe. Future telescopes, particularly the James Webb Space Telescope, are designed to push even deeper into cosmic history, potentially detecting the very first galaxies to form in the universe. These primordial systems would have been composed almost entirely of hydrogen and helium, the only elements available in the early universe. The first stars to form within these galaxies would have been massive, short-lived objects that quickly enriched their surroundings with heavier elements through supernova explosions. The James Webb Space Telescope, with its unprecedented infrared sensitivity and resolution, has already begun to revolutionize our understanding of the early universe. Its observations have revealed galaxies that are larger, more massive, and more mature than expected at very early cosmic times. Some galaxies observed by Webb appear to have formed their stars more efficiently than theoretical models predict, suggesting that galaxy formation in the early universe may have proceeded more rapidly than previously thought. The distribution of galaxies within the observable universe reveals the cosmic web on its largest scales. Surveys mapping millions of galaxies show that the filamentary structure we observe in our cosmic neighborhood extends as far as we can see. The cosmic web appears to be a universal feature, with galaxies tracing dark matter filaments that stretch across billions of light years and connect the densest regions of space. These large-scale surveys have revealed that cosmic structure follows a hierarchical pattern, with small structures forming first and then merging to create larger ones. Galaxy clusters represent the largest gravitationally bound structures in the universe, while superclusters and the cosmic web represent even larger scale patterns that are not gravitationally bound, but are shaped by the overall distribution of matter and dark energy. On the largest observable scales, the universe appears remarkably homogeneous and isotropic, meaning it looks essentially the same in all directions and at all locations. This cosmic principle forms one of the foundational assumptions of modern cosmology and is supported by observations showing that the properties of the cosmic microwave background and the distribution of distant galaxies are consistent across the entire sky. However, this homogeneity only emerges when we consider sufficiently large scales. On smaller scales, the universe is highly structured, with matter concentrated into galaxies, clusters, and filaments separated by vast voids. The scale at which the universe transitions from inhomogeneous to homogeneous is roughly 500 million light-years, beyond which the density of matter becomes essentially uniform throughout space. This transition to homogeneity represents a fundamental property of the universe and provides important constraints on theories of cosmic evolution. The scale of homogeneity is related to the distance that matter could have traveled or been influenced by causal processes since the Big Bang. Structures larger than this scale must have originated from initial conditions rather than from processes occurring after the universe began. The observable universe contains an estimated 2 trillion galaxies, though this number represents our current best estimate and may change as our observational capabilities improve. Each of these galaxies contains billions or trillions of stars, suggesting that the total number of stars in the observable universe may exceed 10 to the 24th power, a number so large that it rivals the estimated number of grains of sand on all the beaches of Earth. Recent deep field observations suggest that the number of galaxies in the observable universe may be even larger than 2 trillion. Many distant galaxies are too faint to detect with current telescopes, and improved sensitivity may reveal additional populations of low luminosity systems. The total number of galaxies that have ever existed may be much larger still, as many small galaxies have likely merged with larger systems over cosmic time. The volume of the observable universe is approximately 4 times 10 to the 80th power cubic meters, a space so vast that it defies comprehension. If we could somehow shrink the observable universe so that the Milky Way became the size of a grain of sand, the observable universe would still be larger than Earth. This comparison helps illustrate the incredible scales involved in cosmic structure, where even our enormous galaxy becomes insignificant compared to the totality of observable space. To put this volume in another perspective, if we filled the observable universe with spheres the size of Earth, we would need roughly 10 to the 77th power of them. If each sphere represented a unique book, and each book contained all of human knowledge, the observable universe could contain more information than has ever been created by our entire civilization, repeated countless trillions of times over. Within this vast volume, the average density of matter is extraordinarily low, roughly equivalent to 5 hydrogen atoms per cubic meter. This means that the vast majority of space is essentially empty, with matter concentrated into tiny islands of structure, scattered across an ocean of vacuum. The universe is far emptier than even the most perfect vacuum achievable in terrestrial laboratories. Yet despite this emptiness, the observable universe contains an enormous amount of matter and energy. The total mass of all galaxies, dark matter, and other forms of matter in the observable universe is estimated to be roughly 10 to the 54th kilograms, equivalent to about 10 to the 23rd solar masses. This represents enough matter to create over 100 billion galaxies similar to the Milky Way. The energy content of the observable universe is dominated by dark energy, which makes up roughly 68% of the total energy density. This mysterious component, responsible for the accelerating expansion of space, represents an energy density of only about 6 times 10 to the minus 10 joules per cubic meter. While this seems incredibly small, when multiplied by the enormous volume of the observable universe, it represents a staggering total energy content. The observable universe also serves as a time machine, allowing us to observe cosmic evolution directly. When we look at a galaxy 1 billion light-years away, we see it as it was 1 billion years ago. By studying galaxies at different distances, astronomers can trace how cosmic structure has evolved over time, observing the assembly of the first galaxies, the peak epoch of star formation roughly 10 billion years ago, and the gradual decline in cosmic activity that has occurred since then. This cosmic archaeology has revealed that the universe was a much more active and violent place in the past. The early universe experienced higher rates of galaxy mergers, more vigorous star formation, and more energetic phenomena like quasars and gamma-ray bursts. As the universe has aged and expanded, these violent processes have gradually subsided, leading to the relatively quiet cosmos we observe today. The peak of cosmic star formation occurred roughly 10 billion years ago, when the universe was about 3 billion years old. During this epoch, galaxies were forming stars at rates several times higher than today, fueled by the abundant gas supplies available in the younger, denser universe. Since then, star formation has gradually declined, as gas becomes depleted and dark energy causes space to expand more rapidly. The study of distant supernovae has provided crucial evidence for the acceleration of cosmic expansion driven by dark energy. By measuring the apparent brightness of Type Ia supernovae at various distances, astronomers discovered that these stellar explosions appeared dimmer than expected if the universe's expansion were decelerating due to gravitational attraction. This unexpected dimness indicates that cosmic expansion has been accelerating for the past 5 billion years. This discovery of cosmic acceleration was so surprising that it earned its discoverers the 2011 Nobel Prize in Physics. The acceleration implies the existence of dark energy, a mysterious component that makes up the majority of the universe's energy density, yet remains completely unknown to physics. Understanding the nature of dark energy represents one of the greatest challenges in modern science. Multiple independent lines of evidence now support the existence of dark energy and cosmic acceleration. Observations of the cosmic microwave background, measurements of galaxy clustering, and studies of distant supernovae all point to the same conclusion. The expansion of the universe has been accelerating for roughly the past 5 billion years. This acceleration appears to be driven by a form of energy with negative pressure, causing space itself to expand exponentially. The cosmic microwave background radiation provides our most direct view of the universe's early conditions and serves as a cosmic laboratory for testing fundamental physics. The precise temperature and polarization patterns in this radiation encode information about the universe's composition, geometry, and early evolution. These measurements have confirmed that space is geometrically flat to extraordinary precision, supporting theoretical predictions from cosmic inflation. The flatness of space has profound implications for the ultimate fate of the universe. In a flat universe dominated by dark energy, cosmic expansion will continue accelerating forever, eventually leading to a cold, empty cosmos, where galaxies become isolated islands, separated by vast distances. Stars will gradually exhaust their nuclear fuel, black holes will slowly evaporate through Hawking radiation, and the universe will approach a state of maximum entropy known as heat death. However, the observable universe represents only a fraction of the total universe, which may be much larger or even infinite in extent. The cosmic microwave background shows no evidence for curvature or edge effects that would indicate we can see a significant fraction of the total universe. Current observations are consistent with a universe that extends far beyond our observable horizon, possibly containing regions with very different properties or even different physical laws. The concept of the observable universe also raises profound questions about the nature of knowledge and reality. Beyond our cosmic horizon lie regions of space that will forever remain unknowable to us, containing galaxies, stars, and possibly life forms that we can never observe or contact. These unreachable realms may contain wonders beyond our imagination, yet they remain as inaccessible as if they existed in separate universes entirely. Future observations will continue to push the boundaries of the observable universe, though we will never exceed the fundamental limit imposed by the finite age of the universe and the speed of light. The James Webb Space Telescope and other next-generation instruments will detect fainter and more distant galaxies, potentially observing the very first stars to form in the universe. These observations will provide crucial tests of our understanding of cosmic evolution and may reveal new phenomena in the early universe. Gravitational wave astronomy has opened an entirely new window on the distant universe, allowing us to detect colliding black holes and neutron stars across cosmic distances. As gravitational wave detectors become more sensitive, they may eventually probe the universe's earliest moments, potentially detecting signals from cosmic inflation itself. Such observations would provide unprecedented insights into the fundamental physics governing the universe's birth and evolution. The study of neutrinos, nearly massless particles that interact very weakly with matter, offers another potential probe of the early universe. The cosmic neutrino background, predicted to permeate all of space, contains information about conditions when the universe was just 1 second old. Though these primordial neutrinos have never been directly detected, future experiments may succeed in observing this relic radiation from the universe's earliest moments. As we contemplate the observable universe in its entirety, we are struck by both its immensity and its limits. This cosmic sphere, containing trillions of galaxies and spanning nearly 100 billion light-years across, represents the totality of everything we can ever hope to observe directly. Yet it may be only a tiny fraction of a much larger or infinite cosmos that extends far beyond our ability to detect. The observable universe stands as a testament to the power of human curiosity and ingenuity. Through careful observation, mathematical reasoning, and technological innovation, we have mapped the cosmos from our local solar system to the very edge of space and time. We have traced cosmic evolution from the first moments after the Big Bang to the present day, revealing a universe far stranger and more wonderful than our ancestors could have imagined. Within this vast cosmic arena, containing more galaxies than there are stars in the Milky Way, we find ourselves on a small planet orbiting an ordinary star in an unremarkable galaxy. Yet it is from this humble vantage point that we have managed to comprehend the universe's grand design, demonstrating that consciousness and intelligence can emerge even in the vast emptiness of space and achieve understanding that spans the cosmos itself. The observable universe represents both the culmination of our cosmic journey and the beginning of even grander mysteries. Beyond its boundaries may lie realms even more vast and complex, regions where our current understanding of physics breaks down and new phenomena await discovery. As we prepare to explore these ultimate frontiers of knowledge, we carry with us the profound realization that we have already traveled, in mind, if not in body, across the entire breadth of observable creation. As we stand at the edge of the observable universe, gazing across nearly 14 billion years of cosmic history, we face one of the most profound questions in all of science. What lies beyond? Past the cosmic microwave background, beyond the farthest galaxies we can ever hope to see, stretches a realm that may dwarf everything we have encountered so far. Here, in the unobservable universe, we enter the domain of theoretical physics and cosmic speculation. The very concept of an unobservable universe challenges our deepest assumptions about knowledge and reality. Throughout human history, we have extended our reach through better tools and techniques, always pushing back the boundaries of the unknown. Yet the horizon of the observable universe represents an absolute limit, imposed not by technological constraints, but by the fundamental structure of space-time itself. This limitation forces us to confront a humbling truth. The totality of everything we can observe may represent only a minuscule fraction of what actually exists. The observable universe, vast as it is with its trillions of galaxies and countless stars, might be like a single drop of water in an infinite ocean, or a grain of sand on an endless beach. The cosmic microwave background radiation provides us with a snapshot of the universe when it was only 380,000 years old, showing us patterns that appear to extend uniformly in all directions. This remarkable uniformity suggests that the universe continues beyond our observational horizon with the same basic properties, the same physical laws, the same types of matter and energy, and the same fundamental structure. This inference is supported by our understanding of cosmic inflation, the theory that the universe underwent a period of exponential expansion during its earliest moments. If inflation occurred as theorized, it would have stretched quantum fluctuations to cosmic scales, creating density variations that extend far beyond our observable horizon. Conservative estimates suggest that the actual universe could be at least 10 to the 23rd times larger than what we can observe. But even these staggering numbers may represent a dramatic underestimate. Many versions of inflation theory suggest that the expansion continued far longer than required, potentially creating a universe that is functionally infinite in extent. In an infinite universe, every possible arrangement of matter and energy that is consistent with the laws of physics would occur not just once, but infinitely many times. The implications of an infinite universe are mind-bending. In such a cosmos, there would exist perfect copies of Earth, of our solar system, and of every person who has ever lived. These duplicates would not be approximate copies, but exact replicas down to the quantum level, living identical lives and making identical choices. Statistical arguments suggest that your nearest identical copy would exist at a distance so vast that it makes our observable universe seem infinitesimally small. Beyond these exact copies, an infinite universe would contain every possible variation and permutation of cosmic structure. There would be Earths where history unfolded differently, where the dinosaurs never went extinct, where evolution took alternative paths. The landscape of possibilities in an infinite universe encompasses everything that can possibly exist, creating a cosmic library containing every story that could ever be told. These ideas lead us into the realm of the multiverse, one of the most speculative yet mathematically rigorous concepts in modern cosmology. The multiverse hypothesis suggests that our observable universe is just one bubble in a vast cosmic foam, where countless other universes exist with potentially different physical laws, constants of nature, and evolutionary histories. The multiverse concept arises naturally from several independent lines of theoretical reasoning. Eternal inflation theory suggests that while inflation ended in our region of space, it continues indefinitely in other regions, constantly creating new bubble universes. String theory predicts an enormous landscape of possible vacuum states, each corresponding to a universe with different physical laws and constants. In the string theory landscape, the number of possible universes may exceed 10 to the 500th power, each with its own unique combination of particle masses, force strengths, and spatial dimensions. Most would be sterile and lifeless, with physical constants that prevent the formation of atoms, stars, or any complex structures. Only a tiny fraction would possess the precise balance of properties necessary for the emergence of complexity and life. This vast landscape provides a potential explanation for one of the deepest mysteries in cosmology: why the physical constants of our universe appear to be fine-tuned for the existence of life. In a multiverse containing countless universes with different physical constants, the apparent fine-tuning becomes less mysterious. We find ourselves in a universe compatible with our existence not because the constants were deliberately chosen, but because we could only have evolved in a universe where such evolution was possible. This anthropic explanation remains controversial among physicists and philosophers. Critics argue that the multiverse hypothesis is unscientific because it makes no testable predictions. Proponents counter that the multiverse arises naturally from our best theories of fundamental physics and provides the most elegant explanation for otherwise inexplicable cosmic coincidences. The debate touches on fundamental questions about the nature of scientific explanation and the role of observation in defining reality. If we can never directly observe other universes, can we legitimately claim they exist? Does the multiverse represent a profound insight into the nature of reality, or is it an untestable speculation that lies beyond the bounds of empirical science? These questions become even more complex when we consider that the unobservable regions of our own universe may contain structures and phenomena that challenge our current understanding of physics. While we assume that the same physical laws operate throughout space, this assumption may not hold in regions vastly larger than anything we can observe. Some theoretical models suggest that the universe could contain structures analogous to the hierarchy we observe from planets to galaxy clusters, but operating on scales billions of times larger. The cosmic web itself might be organized into larger scale patterns that we cannot perceive from our limited vantage point. Another possibility involves the ultimate fate of cosmic expansion. While we observe that expansion is currently accelerating due to dark energy, we cannot know with certainty what will happen in the far future. Dark energy might remain constant forever, or it might decay and change its properties, potentially leading to a reversal of cosmic expansion. Some speculative theories suggest that cosmic expansion might be cyclical, with periods of expansion followed by contraction in an endless series of big bangs and big crunches. In such a scenario, our current universe would be just one cycle in an eternal sequence, with previous universes having existed before the Big Bang and future universes destined to arise after our cosmos ends. The search for indirect evidence of physics beyond our cosmic horizon represents one of the most challenging frontiers in theoretical cosmology. While we cannot directly observe the unobservable universe, it might still leave subtle imprints on the regions we can see. Some cosmologists have searched for evidence of collisions between our cosmic bubble and neighboring bubble universes during the inflationary epoch. The quantum mechanical nature of reality adds another layer of mystery to the unobservable universe. Some theories propose that quantum fluctuations could spontaneously create new regions of space and time, leading to a fractal or branching structure of reality, where new universes constantly bubble into existence. These considerations lead us to perhaps the most profound question raised by the concept of the unobservable universe. What does it mean for something to exist if it can never be observed or measured? The history of physics has repeatedly shown that reality extends far beyond our direct sensory experience. From atoms and electromagnetic fields to black holes and dark matter, the unobservable universe challenges us to take this expansion of perspective to its logical extreme. If the laws of physics that operate in our cosmic neighborhood extend throughout space, then the unobservable regions should contain the same types of structures and processes we see nearby. The key philosophical question is whether mathematical consistency and logical inference constitute sufficient evidence for existence, even in the absence of direct observational confirmation. Many physicists argue that if our best theories predict the existence of unobservable regions with specific properties, we should take these predictions as seriously as any other scientific hypothesis. The unobservable universe also raises questions about the future of scientific discovery. If we have already mapped the largest structures we can ever hope to see, what new frontiers remain for cosmic exploration? The answer may lie not in observing more distant objects, but in understanding more fundamental aspects of the structures we can already see. The search for life beyond Earth also represents a frontier that extends into the unobservable universe. If life exists elsewhere in our cosmic neighborhood, it almost certainly exists in countless locations throughout the unobservable regions as well. Advanced civilizations might have developed technologies that allow them to probe deeper into the nature of reality than we currently can. The possibility that intelligence might emerge throughout the unobservable universe raises fascinating questions about the cosmic significance of consciousness and knowledge. If observers exist in countless locations throughout space and time, the universe might be far more aware of itself than we typically imagine. Yet the unobservable universe reminds us that our knowledge, however impressive, remains bounded by fundamental limits. Beyond our cosmic horizon lies a realm that may contain wonders beyond our wildest imagination, structures and phenomena that would revolutionize our understanding of reality if we could only observe them. The unobservable universe thus serves as both a frontier and a mirror, reflecting our deepest questions about existence, knowledge, and the nature of reality itself. It challenges us to think beyond the limits of observation while remaining grounded in the mathematical precision of physical law. It reminds us that the cosmos extends far beyond anything we can ever hope to see, while inspiring us to continue pushing the boundaries of what we can understand. Among all the discoveries that have shaped our understanding of the cosmos, perhaps none has been more revolutionary than the realization that the universe itself is growing larger with each passing moment. This expansion represents not the movement of galaxies through space, but the stretching of space itself, carrying everything within it farther apart in a cosmic dance that has been unfolding for nearly 14 billion years. For centuries, astronomers and philosophers alike had assumed that the universe was essentially unchanging on the largest scales. This view seemed so natural that even Albert Einstein included a cosmological constant in his theory to prevent his equations from predicting a universe that changed over time. The first hints that this picture might be wrong came from observations of spiral nebulae in the 1910s and 20s. Astronomers like Vesto Slipher discovered that the light from most of these objects was shifted toward longer, redder wavelengths, suggesting they were moving away from us at high speeds. The breakthrough came through Edwin Hubble's work at Mount Wilson Observatory. Using the 100-inch Hooker telescope, Hubble resolved individual stars in nearby spiral nebulae and determined their distances using Cepheid variable stars. What he found revolutionized our understanding of the cosmos. Not only were these spiral nebulae actually distant galaxies, but they were all moving away from us. More remarkably, Hubble discovered a relationship between distance and recession velocity. The farther away a galaxy was, the faster it appeared to be moving away from us. This relationship, now known as Hubble's law, provided the first direct evidence that the universe as a whole was expanding. The expansion of the universe is often misunderstood as galaxies flying apart through empty space, like debris from an explosion. This mental picture is fundamentally incorrect. The expansion does not occur within space, but rather represents the stretching of space itself. Galaxies are not moving through the universe. Instead, the universe is growing larger, carrying the galaxies along with it. To visualize this concept, imagine the surface of a balloon being inflated. As the balloon expands, points marked on its surface move away from each other, not because they are traveling across the surface, but because the surface itself is stretching. Every point on the balloon observes the same pattern of recession, illustrating that cosmic expansion has no center. The rate of cosmic expansion is characterized by the Hubble constant, approximately 70 kilometers per second per megaparsec. This means that for every 3.3 million light-years of distance, galaxies are receding an additional 70 kilometers per second faster. While this seems modest, galaxies at the edge of our observable universe are receding at velocities approaching the speed of light. Measuring the Hubble constant has proven remarkably challenging, leading to what cosmologists call the Hubble tension. Different methods give slightly different values, with discrepancies larger than measurement uncertainties can explain. This tension may indicate new physics beyond our current understanding. The expansion of the universe has not been constant over cosmic time. During the first fraction of a second after the Big Bang, the universe underwent cosmic inflation, a period of exponential expansion that stretched space by an enormous factor. This brief but dramatic epoch solved several cosmological puzzles and created the density variations that eventually grew into galaxies and galaxy clusters. After inflation ended, the universe entered a period of more gradual expansion, driven by matter and radiation. For several billion years, cosmic expansion gradually slowed down as gravity worked to pull matter together. This deceleration was expected based on our understanding of gravity's attractive effects. However, observations in the late 1990s revealed one of the most surprising discoveries in cosmology. Cosmic expansion is not slowing down, but is instead accelerating. Studies of distant Type Ia supernovae showed these stellar explosions appeared dimmer than expected, indicating they were farther away than models assuming decelerated expansion predicted. The discovery of cosmic acceleration earned its discoverers the 2011 Nobel Prize in Physics. The acceleration implies the existence of dark energy, a mysterious form of energy that acts as a cosmic repulsive force. Dark energy appears to make up roughly 68% of the universe's total energy density. Dark energy behaves very differently from any form of matter or energy we understand. While ordinary matter becomes less dense as the universe expands, dark energy maintains constant density even as space grows larger. This means that as the universe expands, the total amount of dark energy increases, providing an ever stronger push that accelerates expansion. The nature of dark energy remains one of the deepest mysteries in modern physics. The simplest explanation is that it represents the energy of empty space itself, but calculations give results that differ from observations by a factor of 10 to the 120th power, making this the worst prediction in theoretical physics history. The current phase of accelerated expansion has profound implications for the future evolution of the universe. If dark energy continues behaving as it does today, cosmic expansion will accelerate exponentially, eventually separating galaxies by such vast distances that they will disappear beyond each other's observational horizons. This scenario leads to a lonely future for any surviving civilizations. Astronomers living trillions of years from now will see a night sky dominated by their local galactic group, with no sign of the rich cosmic web we observe today. They will have lost the ability to study cosmic expansion and most evidence of the universe's dynamic history. The study of cosmic expansion has revealed that the universe undergoes phase transitions where different forms of energy dominate its evolution. After inflation, radiation dominated for tens of thousands of years, then matter dominated for billions of years, and finally dark energy began dominating about 5 billion years ago. These transitions can be understood by how different forms of energy dilute as the universe expands. Radiation density decreases rapidly due to cosmological redshift. Matter density decreases more slowly, while dark energy density remarkably remains constant, eventually overwhelming both matter and radiation. The expansion also affects how we observe distant objects. Light from distant galaxies is stretched by cosmic expansion, shifting it toward longer wavelengths through cosmological redshift. This is why infrared telescopes like the James Webb Space Telescope are crucial for studying the early universe. Understanding cosmic expansion requires sophisticated mathematical models based on Einstein's theory of general relativity. These models relate the expansion rate to the universe's energy content and successfully explain a wide range of cosmic phenomena through the Standard Model of Cosmology. Future observations will continue testing our understanding of cosmic expansion. Gravitational wave astronomy offers a completely new way to study expansion by measuring cosmic distances independently of traditional methods. The discovery of dark energy has also opened new frontiers in fundamental physics, suggesting our understanding of space, time, and gravity may be incomplete. As we contemplate the expansion of the universe, we are confronted with the dynamic nature of existence itself. The cosmos is not a static stage, but an active participant in its own evolution. Space and time are not merely coordinates, but evolving entities that grow, stretch, and change as the universe ages. This represents one of the most profound shifts in human understanding since the Copernican revolution. We live not in an eternal, unchanging cosmos, but in a universe with a definite beginning, complex history, and uncertain future. We happen to live during a golden age of cosmology, when the universe retains evidence of its dynamic history, while remaining young enough for us to discover and understand cosmic expansion. As we contemplate the vast expanse of the cosmos and its ongoing expansion, we encounter one of the most profound questions in all of cosmology. What is the shape of the universe itself? This question probes deeper than asking about the arrangement of galaxies or cosmic filaments. Instead, it asks about the fundamental geometry of space and time, the very fabric upon which all cosmic events unfold. When we speak of the universe's shape, we are not referring to its appearance from some external vantage point, for there is no outside perspective from which to view the cosmos as a whole. Instead, we are asking about the intrinsic geometry of space itself, the way that distances, angles, and volumes relate to each other across the vast scales of the universe. The question of cosmic geometry emerged naturally from Einstein's theory of general relativity, which revealed that space and time are not merely passive stages upon which physical events occur, but are dynamic entities that can bend, stretch, and curve in response to matter and energy. In Einstein's universe, massive objects warp the fabric of space-time around them, creating the effects we observe as gravity. The mathematics of general relativity reveals that the universe can have one of three basic geometric shapes, depending on its total energy density. These three possibilities represent fundamentally different types of space, each with unique properties and implications for cosmic evolution. The first possibility is a flat universe, where the geometry of space follows the familiar rules of Euclidean geometry. In flat space, parallel lines never meet. The angles of a triangle always add up to exactly 180 degrees, and the circumference of a circle is always exactly pi times its diameter. A flat universe would extend infinitely in all directions, with no edges or boundaries. The second possibility is a closed universe, where space curves back on itself, like the surface of a sphere. In this geometry, parallel lines eventually converge, triangle angles add up to more than 180 degrees, and a circle's circumference is less than pi times its diameter. Most remarkably, a closed universe would be finite in size, but have no edges or boundaries. A traveler could journey in any direction, indefinitely, and eventually return to their starting point. The third possibility is an open universe, where space curves away from itself, like a saddle shape. In this geometry, parallel lines diverge from each other, triangle angles add up to less than 180 degrees, and a circle's circumference is greater than pi times its diameter. An open universe would be infinite in extent, with distinctive, negative curvature affecting the behavior of light and matter. These three geometric possibilities correspond to different amounts of matter and energy in the universe. A flat universe requires exactly the critical density needed to balance expansion against gravitational collapse. A closed universe contains more than the critical density, creating enough gravitational attraction to eventually halt expansion and reverse it. An open universe contains less than the critical density, allowing expansion to continue forever. For decades after Einstein formulated his theory, astronomers struggled to determine which possibility described our actual universe. The challenge lay in measuring the total density of matter and energy with sufficient precision to distinguish between the three scenarios. The breakthrough came from detailed studies of the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. This ancient light carries within its subtle temperature variations the signatures of cosmic geometry. The size and distribution of hot and cold spots depend critically on whether space is flat, open, or closed. When space is flat, sound waves in the early universe would have traveled specific distances before the cosmos became transparent to light. These sound horizons would appear as characteristic patterns in the cosmic microwave background. If space were curved, these patterns would appear either larger or smaller than expected, revealing the underlying geometry. The Cosmic Background Explorer, Wilkinson Microwave Anisotropy Probe, and Planck Satellite measured these patterns with extraordinary precision, revealing the geometry of the universe with unprecedented accuracy. The results were both surprising and elegant. The universe appears to be flat, to within measurement, uncertainties. The patterns in the cosmic microwave background match almost exactly what would be expected for a perfectly flat geometry, with any curvature being smaller than current instruments can detect. This represents one of the most precise determinations of a fundamental cosmic property, revealing that we live in a universe balanced exactly at the critical density. The flatness of the universe has profound implications for cosmic evolution and ultimate fate. In a flat universe dominated by dark energy, expansion will continue accelerating forever, carrying galaxies apart at an ever-increasing rate. Unlike a closed universe that would eventually recollapse, our flat universe will expand exponentially, approaching a state of maximum entropy, known as heat death. The discovery of cosmic flatness also provided strong support for the theory of cosmic inflation, which naturally explains why the universe should have exactly the critical density. During the inflationary epoch, any initial curvature would have been stretched to undetectable levels, leaving behind a universe that appears flat on all observable scales. However, the determination that our universe is flat refers only to its overall average geometry. On smaller scales, the universe is far from flat, with matter and energy creating local curvatures in space-time that we observe as gravitational fields. Every star, planet, and galaxy warps space around itself, creating regions of positive curvature where gravity is strong. The interplay between local curvature and global geometry creates a rich tapestry of space-time structure throughout the cosmos. Near massive objects like black holes, space-time curvature becomes so extreme that it can trap light itself. In the vast spaces between galaxies, curvature is minimal, and space approaches the flat geometry predicted by cosmic observations. Understanding the universe's shape also requires considering not just spatial geometry, but the structure of space-time itself. Einstein's theory reveals that space and time are intimately connected, forming a four-dimensional continuum where the curvature of space is inseparable from the flow of time. The measurement of cosmic geometry has revealed important constraints on the fundamental constants of nature. The flatness of space requires a precise balance between different forms of energy in the universe, including ordinary matter, dark energy, and radiation. This fine-tuning raises deep questions about the nature of physical laws and the possibility of other universes with different properties. The question of cosmic topology adds another layer of complexity to understanding the universe's shape. Even in a flat universe, space could have a complex topological structure, affecting the global connectivity of the cosmos. Several possible topologies have been proposed, including toroidal shapes where opposite edges are connected, creating a cosmic donut. Searches for topological signatures in cosmic observations have so far yielded no definitive evidence for non-trivial topology. The universe appears consistent with simple, infinite flat geometry, though more complex topologies remain possible if they operate on scales larger than our observable horizon. The study of cosmic geometry has also revealed the importance of dark energy in determining the universe's shape and fate. While total matter density determines spatial curvature, dark energy affects expansion dynamics and ultimate evolution. If dark energy behaves as a cosmological constant, cosmic expansion will continue, accelerating exponentially forever. The possibility of changing dark energy introduces concepts like phantom energy, which would grow stronger over time, eventually overwhelming all other forms of matter and energy and tearing apart space-time itself in a scenario known as the Big Rip. The shape of the universe also raises profound philosophical questions about the nature of existence and infinity. If the universe is truly infinite, as suggested by its flat geometry, then it contains an infinite amount of matter and energy distributed across endless expanses of space. In an infinite universe, every possible arrangement of matter would occur not just once, but infinitely many times. As we contemplate the shape of the universe, we are confronted with the remarkable precision and elegance of cosmic geometry. The universe appears balanced exactly at the critical point between expansion and collapse, creating a flat geometry that extends infinitely in all directions. This flatness likely reflects the fundamental processes that shaped the cosmos during its earliest moments. The study of cosmic shape represents one of humanity's greatest intellectual achievements, revealing through mathematical analysis and precise observation the hidden geometry of existence itself. Yet the question remains far from fully answered, as hidden curvatures might exist on scales larger than our observable horizon, and the geometry itself might evolve over cosmic time in ways we do not yet understand. As our cosmic journey has taken us from the familiar scales of our solar system to the edge of the observable universe and beyond, we have relied on humanity's remarkable ability to measure and quantify the cosmos. Through ingenious techniques and increasingly sophisticated instruments, we have mapped distances spanning dozens of orders of magnitude. Yet as we push ever deeper into cosmic mysteries, we begin to encounter fundamental limits that constrain not just our current capabilities, but the very possibility of measurement itself. These limits arise not from technological inadequacies that might someday be overcome, but from the basic structure of physical reality. They emerge from the quantum nature of matter and energy, the finite speed of light, the expansion of space, and the discrete nature of information itself. The most fundamental limitation on cosmic measurement stems from the quantum mechanical nature of reality itself. At the smallest scales, the act of measurement inevitably disturbs the system being observed, creating an inherent uncertainty that cannot be eliminated through better instruments or more careful techniques. The famous uncertainty principle tells us that we cannot simultaneously know both the exact position and momentum of any particle with perfect precision. When astronomers measure the position of a distant star or galaxy, they are fundamentally limited by the quantum nature of the photons carrying information from that object. Each photon represents a quantum of information, and the finite number of photons available during any observation creates fundamental statistical limitations on measurement precision. The quantum nature of light also creates fundamental limits on our ability to resolve fine details in cosmic objects. The wavelength of light sets a basic scale below which no optical instrument can distinguish separate features, regardless of its size or sophistication. This diffraction limit means that even a telescope the size of Earth could not resolve features smaller than roughly 1/10 of an arcsecond on nearby stars. These quantum limitations become particularly significant when we try to study the earliest moments of cosmic history. The cosmic microwave background radiation provides our most direct view of the universe when it was only 380,000 years old, but quantum effects during the measurement process introduce unavoidable noise that limits our ability to detect subtle patterns in this ancient light. The expansion of the universe itself creates another fundamental barrier to cosmic measurement. As space expands, the most distant galaxies are carried away from us at velocities approaching or even exceeding the speed of light. Eventually, galaxies become so distant that their light is redshifted beyond the capability of any conceivable detector to measure. This cosmological redshift creates an absolute observational horizon, beyond which no electromagnetic signals can ever be detected. The finite age of the universe imposes perhaps the most absolute limit on cosmic observation. Since the universe began approximately 13.8 billion years ago, light from the most distant objects has had only that amount of time to travel toward us. This creates a fundamental horizon beyond which we can never see, not because of technological limitations, but because the light simply has not had time to reach us since the universe began. This particle horizon represents the ultimate boundary of the observable universe, but it is not a fixed barrier. As time passes, light from more distant regions gradually reaches us, slowly expanding our observable horizon. However, the accelerating expansion driven by dark energy means that this expansion of our observable universe is slowing down and will eventually stop. The discrete nature of information itself creates another fundamental limitation on cosmic measurement. Information can only be transmitted and stored in discrete units, whether as digital bits or as quantum states. The total amount of information that can be extracted from any region of space is limited by the number of quantum states available within that region, related to the holographic principle in theoretical physics. The speed of light creates additional constraints on cosmic measurement. When we observe a galaxy 10 billion light-years away, we see it as it was 10 billion years ago. We cannot know what that galaxy looks like today, because that information will not reach us for another 10 billion years. This means our observations necessarily represent a patchwork of images from different cosmic epochs. The statistical nature of cosmic measurement introduces another layer of fundamental limitations. Many cosmic phenomena are inherently random or chaotic, governed by quantum fluctuations or complex nonlinear dynamics that make precise prediction impossible, even in principle. The formation of individual stars, the detailed structure of turbulent gas flows, and the exact timing of supernova explosions all contain elements of fundamental unpredictability. The complexity of cosmic systems often overwhelms our computational capabilities, creating practical limits that may be as insurmountable as fundamental physical constraints. The three-body problem in celestial mechanics provides a classic example. While we can solve exactly for two gravitationally interacting bodies, adding just one more creates a system whose behavior is fundamentally unpredictable over long time periods. These limitations become particularly acute when studying dark matter and dark energy, which interact only weakly or not at all with ordinary matter and electromagnetic radiation. Dark matter reveals itself primarily through gravitational effects, providing only indirect information about its properties. The weakness of gravitational interactions means that detecting dark matter requires extremely sensitive instruments and long observation times. The measurement of cosmic distances faces particularly severe fundamental limitations. The cosmic distance ladder accumulates uncertainties at each step, with small errors in nearby measurements propagating to create larger uncertainties for distant objects. The discrete nature of suitable calibrating objects also limits precision, as Cepheid variable stars and Type Ia supernovae show intrinsic scatter in their properties. Atmospheric and instrumental effects add additional layers of measurement limitations. Earth's atmosphere constantly distorts observations through turbulence and scattering, while space-based observatories face limitations from cosmic ray damage and thermal fluctuations. The digital nature of modern detectors introduces quantization errors, and the finite bandwidth of any detection system creates additional constraints. The storage and processing of cosmic measurement data faces exponential growth in volume and complexity. Modern sky surveys generate petabytes of data that must be processed and analyzed, threatening to overwhelm our ability to extract meaningful scientific results. Machine learning techniques offer some hope, but introduce their own limitations and biases. The interpretation of cosmic measurements often depends on theoretical models that contain their own uncertainties and limitations. Our understanding of stellar evolution and galaxy formation relies on complex simulations that make approximations about physical processes we do not fully understand. The fundamental constants of nature themselves are known only to finite precision, carrying uncertainties that propagate through all astronomical calculations. Looking toward the future, some measurement limitations may be overcome through technological advances, while others represent absolute barriers that no amount of progress can surmount. The fundamental constraints imposed by quantum mechanics, relativity, and the finite age and expansion of the universe will persist regardless of technological development. The recognition of these fundamental limits does not diminish the value of cosmic measurement, but provides crucial context for understanding what we can and cannot hope to learn about the universe. These limitations define the boundaries of empirical science and help distinguish between questions that might someday be answered and those that may forever remain beyond our reach. Perhaps most importantly, these limits remind us that our knowledge of the universe, however impressive, will always remain incomplete. The cosmos holds secrets that we may never unlock, not because of failures in human capability, but because of the fundamental structure of reality itself. This humbling recognition should inspire both continued efforts to push against our limitations and philosophical reflection on the nature of knowledge in an infinite and mysterious universe. As we stand at the culmination of our cosmic journey, having traveled from the familiar confines of our solar system to the very edges of observational possibility, we face the ultimate question that has haunted human consciousness since we first gazed up at the stars. Is the universe infinite? This question cuts to the heart of existence itself, challenging our deepest assumptions about space, time, and the nature of reality. The concept of infinity has puzzled human minds for millennia. Ancient philosophers struggled with paradoxes involving infinite division and endless expansion. Mathematicians developed elaborate frameworks for handling different types of infinity, discovering that some infinities are larger than others, in ways that defy intuition. Physicists have found infinity appearing in their equations as both a useful mathematical tool and a troubling sign that their theories may be incomplete. When we ask whether the universe is infinite, we are really asking several related but distinct questions. Is space infinite in extent, stretching endlessly in all directions? Does time extend infinitely into the past and future? Are there infinite numbers of galaxies, stars, and planets scattered throughout the cosmos? Each of these questions probes different aspects of cosmic infinity and may have different answers. Our observations provide tantalizing clues but no definitive answers. The cosmic microwave background radiation appears remarkably uniform across the entire sky, suggesting that the universe extends far beyond our observable horizon with similar properties. The geometry of space appears to be flat, which is consistent with infinite spatial extent. Yet these observations only tell us about the observable universe, that finite bubble of space and time from which light has had time to reach us since the Big Bang. Beyond our cosmic horizon may lie regions of space that are fundamentally similar to what we observe nearby, containing similar galaxies, stars, and perhaps even life. If the laws of physics are truly universal, then the processes that created structure in our cosmic neighborhood should operate throughout all of space, potentially creating an infinite hierarchy of cosmic architecture, extending in all directions forever. The implications of an infinite universe are staggering and counterintuitive. In an infinite cosmos containing infinitely many galaxies, every possible arrangement of matter that is consistent with the laws of physics must occur not just once, but infinitely many times. This leads to the remarkable conclusion that there would exist perfect duplicates of every person, every world, and every cosmic structure, scattered throughout the endless expanse of space. Statistical arguments suggest that in an infinite universe, your nearest exact duplicate would exist at a distance so vast that it makes our entire observable universe seem infinitesimal by comparison. This duplicate would not be merely similar to you, but would be identical down to the quantum level, living an identical life and making identical choices. Beyond this nearest copy would lie infinitely many other versions of yourself, some exactly identical, and others representing every possible variation of your life and circumstances. The multiverse theories that emerge from cosmic inflation and quantum mechanics paint an even more extraordinary picture of cosmic infinity. If inflation is eternal, constantly creating new regions of space with potentially different physical properties, then our observable universe represents just one bubble in an infinite cosmic foam. Each bubble might contain its own version of physics, its own constants of nature, and its own evolutionary history. String theory suggests that the number of possible universes might exceed 10 to the 500th power, each with unique combinations of particle masses, force strengths, and spatial dimensions. Most of these universes would be sterile and lifeless, but in an infinite multiverse, even universes capable of supporting complexity and life would exist in infinite numbers, each exploring different pathways of cosmic evolution. The infinite question also touches on the deepest problems in theoretical physics. When infinities appear in physical equations, They often signal that our theories are incomplete or being pushed beyond their domain of validity. Yet infinity may also represent a fundamental aspect of reality that we must learn to accept and incorporate into our theories. The relationship between mathematical and physical infinity remains one of the most profound puzzles in science. Mathematics allows us to manipulate infinities with precision and rigor, but whether these mathematical constructs correspond to physical reality remains unclear. Can something be truly infinite in the physical world, or is infinity merely a useful mathematical idealization? The infinite question also raises fundamental issues about the nature of scientific knowledge and the limits of empirical investigation. If the universe is infinite, then the vast majority of it will forever remain beyond our observational reach. This observational limitation means that the question of cosmic infinity may never be definitively resolved through direct measurement. The search for indirect evidence of cosmic infinity continues through multiple approaches. Precision measurements of the cosmic microwave background might reveal subtle signatures of infinite spatial curvature or topology. Studies of cosmic structure could uncover patterns that extend beyond our observable horizon. Future gravitational wave observations might detect signals from cosmic processes operating on scales larger than anything we can currently observe. The philosophical implications of cosmic infinity extend far beyond science into questions of meaning, purpose, and human significance. In an infinite universe, everything that can happen will happen infinitely many times. Every possible story will be told, every possible life will be lived, and every possible outcome will be realized somewhere in the endless expanse of space and time. This cosmic perspective can be both liberating and terrifying. On one hand, it suggests that consciousness and intelligence are not cosmic accidents, but inevitable consequences of infinite possibility. On the other hand, infinity can make individual existence seem meaningless, reducing each life to an infinitesimal point in an ocean of endless repetition. The infinite question also challenges our concepts of uniqueness and identity. If perfect copies of every person exist throughout an infinite cosmos, what makes any individual truly unique? Are you the only real version of yourself, or are you one of infinitely many equally real copies? These questions probe the deepest foundations of consciousness and personal identity. Religious and spiritual traditions have long grappled with concepts of infinity, often associating it with the divine or transcendent. The idea of an infinite universe can be seen as either supporting or challenging traditional notions of cosmic purpose and design. Some find in cosmic infinity evidence of unlimited creative potential, while others see it as incompatible with concepts of divine plan or ultimate meaning. The practical implications of cosmic infinity remain largely theoretical, since we can only interact with the finite portion of the universe within our causal reach. However, the mere possibility of infinite extent changes how we think about our place in the cosmos and the significance of our actions. Current cosmological models remain agnostic about cosmic infinity, acknowledging it as a possibility, while recognizing the observational limitations that prevent definitive conclusions. The standard model of cosmology is consistent with either finite or infinite spatial extent, depending on details of cosmic topology and the behavior of dark energy over cosmic time. Future theoretical developments might provide new insights into the infinite question. Advances in quantum gravity could reveal whether space-time itself has a discrete or continuous structure at the smallest scales. Better understanding of dark energy might predict whether cosmic expansion will continue forever or eventually reverse. The infinite question represents the ultimate frontier of human knowledge, a boundary where science meets philosophy and observation gives way to imagination. It reminds us that despite our remarkable progress in understanding the cosmos, fundamental mysteries remain that may challenge human comprehension for generations to come. Perhaps the most profound aspect of the infinite question is how it illuminates the extraordinary nature of our finite existence within what may be an infinite cosmos. We are finite beings with finite lifespans, finite knowledge, and finite capabilities. Yet we can contemplate infinity and begin to understand our place within it. This capacity for infinite contemplation within finite minds represents one of the most remarkable features of consciousness and intelligence. The infinite question will likely persist as long as consciousness exists to contemplate it. Future civilizations may probe deeper into cosmic structure and uncover new evidence bearing on cosmic infinity. Yet the fundamental mystery may remain, serving as an eternal reminder that reality extends beyond what any finite mind can fully encompass. In the end, the infinite question teaches us humility. No matter how much we learn about the universe, how far our telescopes can see, or how sophisticated our theories become, we remain finite explorers in what may be an infinite cosmos. This perspective should inspire both wonder at the vastness that surrounds us and appreciation for the remarkable journey that has brought us to this moment of cosmic contemplation. As our cosmic journey draws to a close, we find ourselves transformed by the voyage we have taken together. We began in familiar territory, standing in a backyard under a starlit sky, wondering about the true size of everything around us. Now, hours later, we have traveled across scales so vast that our starting point seems like a distant memory, a tiny speck in an ocean of cosmic immensity. We have journeyed from the comfortable boundaries of our solar system to the edge of the observable universe, where ancient photons have traveled for nearly 14 billion years to reach our telescopes. We have explored the architecture of our galaxy with its 100 billion stars, ventured into the cosmic web that connects galaxies across hundreds of millions of light years, and contemplated realms beyond observation, where infinity itself may reign supreme. The numbers we have encountered challenge the very limits of human comprehension. We have spoken of distances measured in trillions upon trillions of miles, of galaxies containing hundreds of billions of stars, of observable horizons spanning tens of billions of light years. We have contemplated timescales that dwarf human history, from the 13.8 billion year age of the universe to the trillions of years that red dwarf stars may continue burning their nuclear fuel. Yet perhaps the most remarkable aspect of our journey is not the vastness we have discovered, but the fact that we could discover it at all. From our small world, using nothing more than careful observation, mathematical reasoning, and human ingenuity, we have mapped the structure of the entire observable universe. We have traced cosmic evolution from the first moments after the Big Bang to the present day, revealing a cosmos far stranger and more wonderful than our ancestors could have imagined. This achievement represents something extraordinary about consciousness and intelligence. We are patterns of matter and energy that have emerged from cosmic evolution, yet we have developed the ability to understand the very processes that created us. We are made of stellar debris, forged in the nuclear furnaces of ancient stars. Yet, we can comprehend the stellar life cycles that manufactured the elements in our bodies. The vast scales we have explored remind us of both our cosmic insignificance and our cosmic significance. We are tiny beyond measure when compared to galaxies, superclusters, and the observable universe itself. Yet our insignificance in scale is matched by our significance in understanding. As far as we know, we represent one of the universe's few attempts to understand itself. Through us, the cosmos has developed eyes to see its own beauty, minds to comprehend its own complexity, and hearts to appreciate its own grandeur. We are neither the center of the universe, as ancient cosmologies proclaimed, nor are we cosmic accidents without meaning or purpose. Instead, we are participants in an ongoing cosmic story, witnesses to and products of 13.8 billion years of cosmic evolution. The journey we have taken reveals the universe as a place of endless complexity and beauty, where simple physical laws give rise to structures of incredible intricacy. From the elegant spiral arms of galaxies to the intricate web of dark matter that scaffolds cosmic structure, the universe displays an aesthetic sensibility that speaks to something deep within human consciousness. The vastness we have explored puts our earthly concerns into cosmic perspective, Every person who has ever lived, every civilization that has risen and fallen, every thought that has been thought, and every dream that has been dreamed, has occurred within this small corner of a vast cosmos. We are all passengers on a small planet orbiting an ordinary star in an unremarkable galaxy, traveling together through space and time. The cosmic perspective also reveals the preciousness of our existence. In a universe dominated by empty space and dark matter, where temperatures approach absolute zero and radiation can sterilize entire worlds, the emergence of complexity, life, and consciousness represents something extraordinary. We exist in a brief moment of cosmic history, when the universe is old enough to have created complex structures, but young enough to retain the warmth and energy necessary for life. Yet our journey has also revealed the limits of knowledge and the persistence of mystery. Beyond the observable universe may lie realms we can never explore. The nature of dark matter and dark energy remains largely unknown. The possibility of infinite space raises questions that may forever challenge human comprehension. These mysteries remind us that the universe retains secrets that may always exceed our ability to understand. This combination of knowledge and mystery provides the perfect backdrop for continued exploration. Each answer we discover leads to new questions. Each scale we master reveals new scales to explore. The universe appears to be inexhaustible in its capacity to surprise and inspire us, offering endless opportunities for discovery and contemplation. Perhaps most importantly, our cosmic journey reminds us that we are part of something much larger than ourselves. The atoms in our bodies were forged in stellar cores. The molecules that enable our biology were assembled in cosmic chemical factories, and the forces that govern our existence operate on scales from quantum to cosmic. We are not separate from the universe, but integral parts of its ongoing evolution. The vastness we have explored should inspire us to dream big, to think beyond the confines of our immediate experience, and to recognize our connection to the deepest structures of reality. We live in a universe that spans scales from the quantum to the cosmic, from the fleeting to the eternal, from the simple to the incomprehensibly complex. As we return from our journey to the edges of space and time, we carry with us a new appreciation for the extraordinary nature of existence itself. The universe stretches beyond our sight and understanding, a vast expanse where every star is a story, every galaxy a universe unto itself, and every moment an opportunity for wonder and discovery. And as we gaze into the night sky, we join a timeless journey toward the infinite, a quest for understanding that connects us to every human who has ever looked up at the stars and wondered about their place in the cosmos. The universe is vast beyond measure, ancient beyond imagination, and beautiful beyond description. And remarkably, against all odds, we are here to witness it all.